Imagine an object so dense that a sugar cube-sized chunk weighs as much as an entire mountain. This is not a fantastical scenario, but rather the reality of a neutron star, one of the most enigmatic and powerful phenomena in the universe. Born from the explosive deaths of massive stars, neutron stars are not mere remnants of these colossal celestial bodies. They are cosmic laboratories where the very laws of physics stretch, bend, and break. These stars are far from ordinary. They hold vital clues about the universe's structure and evolution, acting as a window into the deepest mysteries of space-time. And yet, the question remains, what happens if two of these extraordinary entities collide? Neutron stars are the incredibly compact remnants of stars that were once much larger than our own sun. Their formation begins with a star burning through its nuclear fuel in an intricate series of fusion stages. These processes churn out heavier elements, each one building on the last until, at the core of the star, iron forms. But when iron appears, the star's fusion process grinds to a halt. Without the energy generated by fusion, the star's core can no longer resist the crushing pull of gravity. At this critical juncture, the outer layers of the star collapse inward in a catastrophic collapse. As gravity intensifies, the core undergoes a remarkable transformation. Protons and electrons combine to form neutrons in an event so violent that it marks the birth of a neutron star. This conversion, occurring under unimaginable pressure, halts the collapse and leads to a star so incredibly dense that it can no longer be comprehended in earthly terms. A neutron star is about 1.5 times the mass of our sun, but its radius is reduced to just the size of a small city. In terms we can understand, imagine squeezing the weight of an entire mountain into a space no larger than a sugar cube. The density of these stars is so intense that a single cubic centimeter of neutron star material could weigh as much as 1 billion tons. The very atoms that form regular matter on Earth no longer exist in their usual forms. Instead of the vast spaces between atomic nuclei, the atoms are crushed so tightly together that they break apart, and neutrons, the building blocks of atomic nuclei, dominate the state of matter. Even more fascinating, many neutron stars spin rapidly, sometimes completing multiple rotations in just a second. In some cases, these rapidly rotating neutron stars emit beams of electromagnetic radiation from their poles, which sweep across space like the beams of a lighthouse. This phenomenon is called a pulsar. These celestial lighthouses emit regular, rhythmic pulses of radiation, allowing astronomers to observe the precise rotation rates of these stars from vast distances. The formation of a neutron star is thus a monumental process, and the journey to their creation is one of the most extreme demonstrations of how a massive star meets its end. To understand the true significance of this event, imagine the entire life cycle of a star. A star much more massive than our sun begins its life by fusing hydrogen into helium in its core. Over millions of years, it produces heavier elements like carbon and oxygen, and eventually the fusion process reaches iron. Once iron forms, the star's core can no longer generate energy from fusion, and gravity causes the core to collapse inward. This catastrophic implosion results in a supernova, an explosion so brilliant it can outshine an entire galaxy, and when the dust settles, what remains is an extremely dense core, potentially the birth of a neutron star. This process is not only fascinating, but also offers a glimpse into the most extreme environments in the universe. The conditions within a neutron star are so extreme that they defy anything we experience on Earth. The mass of a neutron star is comparable to that of a sun-sized star, yet it is compressed into a sphere only a few miles in diameter. In these stars, gravity reigns supreme, pulling every particle together to form an unrelenting density that defies the very fabric of space-time. This unique density is why neutron stars are often referred to as one of the densest objects in the universe. To visualize this, consider the immense gravitational forces at work. A teaspoon of neutron star material weighs more than the entire mass of Mount Everest. This mind-boggling density is the result of the extreme gravitational pull that squeezes the remaining matter into a very small space, making it one of the most compact objects in nature. As if their density weren't extreme enough, neutron stars are also known for their incredibly powerful magnetic fields. These magnetic fields are billions of times stronger than Earth's magnetic field, When these powerful fields interact with the star's rapid rotation, they produce incredibly high-energy radiation that bursts out in regular intervals, often forming what we know as pulsars. These cosmic beacons of energy are not only a marvel to observe, but they also provide us with crucial insights into the behavior of matter under such intense physical conditions. The gravitational pull of a neutron star is equally extraordinary. If you were to stand on its surface, you would experience gravity that is many times stronger than the gravity we feel here on Earth. This means that objects would weigh far more than they do on our planet, something on the scale of a few billion times heavier. This intense gravitational force warps the fabric of space-time itself, creating an environment where time behaves differently. Clocks near a neutron star tick slower than those further away, a phenomenon predicted by Einstein's theory of general relativity. The environment around a neutron star is one of extreme physics. Every moment spent near such a star is a reminder of the universe's vast potential for unknown, incomprehensible phenomena. The matter within a neutron star is unlike anything we can experience on Earth. So compressed, so warped by gravity that even the fundamental laws of nature are stretched to their limits. Understanding these stars and the violent process that leads to their formation can offer us unparalleled insights into how the universe works, from the nature of gravity to the behavior of matter under extreme conditions. In many ways, neutron stars are the universe's extreme laboratories, where the very building blocks of reality are pushed to their absolute limits. Every discovery we make about them teaches us more about the fundamental forces that govern the cosmos, and perhaps most intriguingly about the next stage in the evolution of massive stars. From their intense magnetic fields to their mind-bending density, neutron stars stand as some of the most fascinating and mysterious objects in our universe, holding the key to many questions that have puzzled astronomers for centuries. What happens when two of these titans collide? The answer to this question may reveal even more secrets about the universe's past, present, and future. Neutron stars are among the most extraordinary objects in the cosmos, existing as remnants of supernova explosions, where the catastrophic collapse of a massive star's core creates an incredibly dense and exotic form of matter. These stars are not merely interesting for their existence. They are symbols of the universe's power to shape extreme environments under the influence of gravity, mass, and the fundamental forces of nature. The events that surround neutron stars, such as gamma-ray bursts, are some of the brightest explosions in the universe, and their influence on their surroundings can be nothing short of spectacular. Neutron stars are born from the violent deaths of stars much larger than our sun. When such stars exhaust their nuclear fuel, they no longer have the energy to counterbalance the immense gravitational pull within them. The result is a colossal collapse of the star's core. If this core is massive enough, yet still below the threshold required to create a black hole, it condenses into a neutron star. This transformation is so intense that the core, originally several times the size of the sun, is crushed into a sphere no larger than a small city. And yet, within this tiny volume, the mass may still be around 1.5 times that of the sun. The outcome is a dense, compact object that holds a remarkable amount of matter in a fraction of the space. This density is truly unfathomable. A small chunk of neutron star material, comparable in size to a sugar cube, would weigh as much as several elephants on Earth. The gravity here is so powerful that it warps the very fabric of space-time itself, affecting everything from the way time flows to how objects move near its surface. The neutron star is held together by this extraordinary gravity, which is counterbalanced by the neutrons themselves. In other words, the pressure exerted by the neutrons prevents the star from collapsing further, creating a delicate equilibrium that keeps it stable, at least for now. On the other hand, when a star's core is massive enough to surpass a certain threshold, the collapse does not halt at the formation of a neutron star. Instead, the core continues to collapse inward, becoming so dense that it forms a black hole, an object whose gravitational pull is so extreme that nothing, not even light, can escape it once it crosses the event horizon. The mass of a black hole can be several times that of the sun, but it is concentrated in an infinitely small point known as a singularity. The gravity around a black hole is far more intense than that of a neutron star, as the singularity at its center causes a concentration of mass so immense that it distorts space-time in ways we cannot fully comprehend. While both neutron stars and black holes share some similarities, such as their incredibly strong gravitational fields, their nature differs fundamentally. A neutron star represents a state of balance, where the force of gravity is counteracted by the pressure of neutrons pushing back, allowing the star to exist as a dense but stable object. In contrast, a black hole is a place where gravity has entirely overcome all other forces, leading to a complete collapse of matter and the breakdown of the laws of physics as we understand them. These two celestial phenomena are both outcomes of stellar evolution, shaped by the interplay of gravity, mass, and time, yet they showcase the astounding variety and complexity of the universe. To understand neutron stars better, we must first explore the life cycle of a typical star. Stars like our Sun live for billions of years, fusing hydrogen into helium in their cores, which produces the light and heat we rely on. But when a star of greater mass runs out of fuel, it can no longer sustain the balance between gravity and pressure. The core implodes, and if the conditions are right, the star may explode in a supernova. What remains after this explosion may either form a neutron star or, if the core is massive enough, collapse into a black hole. Neutron stars are incredibly dense, so much so that a sugar cube-sized amount of neutron star material would weigh as much as an entire mountain on Earth. This extreme density arises from the collapse of the star's core, which causes protons and electrons to merge into neutrons. This process creates a state of matter that does not exist anywhere else in the universe. Neutron stars are thus composed almost entirely of these tightly packed neutrons, forming a type of matter that is so unusual and dense that it challenges our understanding of physics. Unlike regular stars, which can span vast distances, neutron stars are relatively small, typically about the size of a large city. But despite their small size, their gravitational pull is enormous. A neutron star's surface gravity is billions of times stronger than Earth's. This intense gravity affects everything that falls onto the surface. It also alters the passage of time. To an observer near the star, time would appear to slow down as they approach its surface. In addition to their extraordinary density and gravity, neutron stars also possess unique magnetic fields, far stronger than those found on Earth. These magnetic fields can be billions of times more powerful than the Earth's, and they play a significant role in shaping the star's behavior. As a neutron star spins, often at incredibly rapid rates, sometimes up to several hundred times per second, its magnetic field interacts with the surrounding space, generating intense beams of radiation that sweep through the cosmos like a cosmic searchlight. If these beams point toward Earth, they appear as flashes of light, making the neutron star appear to pulse regularly. These flashing pulses of energy are what we observe as pulsars. Pulsars, which are essentially rotating neutron stars, are some of the most intriguing phenomena in the universe. As the beams of radiation sweep past Earth, they produce regular flashes of light, often with remarkable precision. This rhythmic pulsing provides us with a reliable cosmic clock, offering valuable insights into the properties of neutron stars and their environment. Neutron stars are also capable of interacting with companion stars in binary systems. In such systems, one star orbits the other, and the neutron star can pull matter from its companion, creating high-energy phenomena such as X-ray bursts. This interaction can cause dramatic changes in the star system, influencing the behavior of both stars. In fact, observing these interactions often reveals more about neutron stars than studying them in isolation. The magnetic fields of neutron stars, combined with their extreme rotation rates, produce a range of fascinating effects. These magnetic fields are responsible for some of the most powerful radiation sources in the universe. As the neutron star spins, its magnetic field can launch jets of energy into space, illuminating regions of the cosmos and creating some of the brightest events observed in our galaxy. These interactions with space itself are a testament to the raw power of these objects and their ability to shape their environments in ways unimaginable. In conclusion, neutron stars are some of the most extraordinary and extreme objects we can study in our quest to understand the universe. With their extreme density, intense gravitational pulls, rapid rotation, and powerful magnetic fields, neutron stars present a unique and fascinating window into the fundamental workings of nature. Their association with high-energy events like gamma-ray bursts and their role in the death cycles of stars make them key players in the ongoing story of the cosmos, standing as both symbols of stellar evolution and gateways to the deeper mysteries of the universe. Moreover, the magnetic fields exert a profound influence on the surface temperature of neutron stars and the matter that is drawn from nearby companion stars. When material from a neighboring star is pulled towards a neutron star, the immense gravitational and magnetic forces at play accelerate the matter to extraordinary speeds as it spirals inward. As it plunges toward the star, this accreting matter builds up an enormous amount of energy, reaching temperatures so high they emit intense X-rays. These X-rays provide vital clues about the neutron star's temperature, magnetic activity, and overall state, offering a glimpse into a world that is beyond the reach of conventional observation. The magnetic fields themselves create a distinctive environment on the surface of a neutron star, warping its shape and influencing the distribution of heat. Regions near the magnetic poles can become intensely hot, while areas further away may remain cooler. This temperature variation can cause the star to exhibit different colors, often emitting light in a range of wavelengths depending on the observer's perspective. The magnetic field of a neutron star is not a passive force, but an active player in shaping the behavior and appearance of these exotic objects. It influences the star's rotation, radiation patterns, and the surrounding environment in ways that make neutron stars among the most dynamic and captivating objects in the universe. In the grand scheme of astrophysics, neutron stars are far more than just fascinating objects. They serve as cosmic laboratories that help scientists explore some of the most extreme conditions in the universe. These stars form when a massive star runs out of fuel and undergoes a catastrophic collapse during a supernova explosion. What remains after this violent event is a dense core made almost entirely of neutrons, subatomic particles that have no electric charge. The immense density of a neutron star is staggering. A neutron star is typically only about 20 kilometers in diameter, yet it can contain more mass than our sun. This remarkable density means that even a small chunk of neutron star material would weigh as much as an entire mountain on Earth. Studying these stars offers an unparalleled opportunity to explore fundamental physics under conditions that cannot be replicated anywhere on Earth. The gravity near a neutron star is so intense that it warps both space and time, offering scientists a unique opportunity to test the theories of gravity proposed by Albert Einstein, particularly his theory of general relativity. Observing the way light behaves near these extreme objects provides crucial insights into how massive objects influence their surroundings, validating or challenging long-standing theories. Furthermore, neutron stars allow researchers to investigate the behavior of matter under extreme densities. The material inside these stars is in a state that is completely inaccessible in terrestrial laboratories, giving scientists a chance to explore how matter behaves when compressed to its utmost limits. By examining the intense magnetic fields and rapid rotation of these stars, scientists can deepen their understanding of nuclear matter and the fundamental forces that shape the universe. Neutron stars are also associated with other remarkable phenomena, such as pulsars. A pulsar is a rotating neutron star that emits beams of radiation in a regular pattern, often in the form of radio waves or X-rays. By studying these pulsations, scientists can gather incredibly precise data that leads to significant breakthroughs in multiple areas of astrophysics, from testing the theories of general relativity to detecting gravitational waves. These rotating beacons of light act as cosmic lighthouses, illuminating the dark and distant corners of the universe and offering insights into the fundamental nature of space, time, and matter. As remnants of massive stars that have reached the end of their life cycles, neutron stars serve as markers of stellar evolution. When a star much larger than our sun exhausts its nuclear fuel, it undergoes a catastrophic collapse in a violent supernova explosion, scattering its outer layers into space and leaving behind a dense, compact core. This core is primarily composed of neutrons, the particles that are tightly packed together under the intense gravitational pressure. The resulting neutron star is only about 20 kilometers in diameter, but it contains more mass than the Sun. The intense gravity around the neutron star also generates powerful magnetic fields, further complicating the star's behavior and appearance. In the context of stellar evolution, neutron stars play a critical role in the recycling of materials throughout the universe. When they form, neutron stars enrich the interstellar medium, the vast, empty space between stars, with heavy elements created during the supernova explosion. These elements later get incorporated into new star formation, perpetuating a cycle of cosmic creation and destruction. Furthermore, when neutron stars are part of a binary system, where they are paired with another star, the neutron star can siphon off material from its companion. This material forms a spinning disk around the neutron star, and in the process it may lead to massive outbursts of energy and light. These dramatic events contribute to the ongoing evolution of our galaxy, shedding light on the complex interactions that govern the lives of stars. Neutron stars also bridge the past and the future in the cosmic narrative, linking the death of one star with the birth of new ones. The collision of two neutron stars, for example, is an event of unimaginable scale and significance. Picture two incredibly dense, compact objects, each about the size of a city but with more mass than the Sun, spinning around one another in a slow, inevitable spiral. As they orbit each other, they lose energy over time, gradually drawing closer. Eventually, the gravitational forces between them become so immense that they collide in a catastrophic event that releases energy far beyond anything we could comprehend. More energy is unleashed in this moment than could be generated by an entire galaxy over the course of a year. This tremendous explosion generates shockwaves that ripple through space, sending out powerful bursts of light and other forms of radiation that can be detected across vast distances of the universe. For observers on Earth, this event can be seen as a brilliant flash of gamma rays, a fleeting but spectacular reminder of the immense power of the cosmos. In the aftermath of such a collision, the combined mass of the two neutron stars forms a new object, which could be another neutron star, or if the mass is large enough, collapse into a black hole. Surrounding this merging site is a vast expulsion of material, much of which is rich in heavy elements such as gold and platinum. These elements, created in the violent death of the neutron stars, are scattered into space, enriching the universe with the building blocks for future star formation and the creation of planets. The merger of neutron stars is not only an event of extraordinary energy, but also a crucial process for the creation of many of the heavy elements that are found on Earth today. Remarkably, these collisions also generate ripples in the fabric of space-time, known as gravitational waves. These waves, which travel across the universe at the speed of light, are a direct consequence of the immense gravitational forces at play during the neutron star merger. When detected, these waves offer a new way to study the universe, providing a window into the dynamics of extreme astrophysical phenomena and allowing scientists to test theories of gravity in ways that were previously impossible. As we continue to observe and study neutron stars and their violent interactions, we uncover ever more about the fundamental laws that govern the universe, expanding our understanding of space, time, and the forces that shape our cosmic existence. Neutron star collisions are among the most dramatic and enigmatic events in the universe, and thanks to advances in technology, scientists can now detect and observe these cosmic phenomena with unprecedented precision. These collisions are not just random explosions in the fabric of space, they are pivotal moments in the life cycle of stars, in the creation of elements, and in our evolving understanding of the cosmos itself. The process by which these cataclysmic events are identified and studied involves a blend of cutting-edge instruments and innovative observational techniques. Neutron stars, the incredibly dense remnants of supernova explosions, are some of the most extreme objects in the universe. When two of these stellar corpses collide, the results are nothing short of spectacular. The energy released in such an event is immense, and the signals they emit provide valuable insights into the fundamental workings of the universe. Detecting and observing the aftermath of these collisions, however, requires highly sensitive technology. The process begins with the detection of gravitational waves, ripples in the fabric of space-time that travel outward at the speed of light when two neutron stars collide. Gravitational wave detectors, such as those operated by the Laser Interferometer Gravitational Wave Observatory, LIGO, and Virgo, are finely tuned instruments that can detect minute changes in the distance between mirrors caused by these passing waves. Even though these gravitational waves may originate from billions of light years away, the detectors can still pick them up with remarkable accuracy. These waves offer scientists a first signal that something extraordinary has happened in a far-off galaxy, a signal that can travel across space undisturbed by interstellar dust and gas. Once the gravitational waves are detected, astronomers can quickly triangulate the location of the collision and direct powerful telescopes toward the region of the sky where the event took place. This is when the next phase of observation begins. These telescopes, both optical and radio, are able to capture the electromagnetic radiation that accompanies a neutron star collision. This radiation can take many forms, including visible light, gamma rays, and radio waves, all of which offer valuable information about the event's characteristics. When two neutron stars collide, the explosion is so intense that it creates a spectacular burst of light known as a kilonova. This explosion is not just a mere flash, it's an incredibly energetic event, releasing enough light to briefly outshine entire galaxies. The visible light from this explosion is accompanied by a variety of other electromagnetic signals, including gamma rays, the most energetic form of light, and radio waves. The gamma ray bursts, GRBs, that result from the collision are brief but extraordinarily powerful, carrying vast amounts of energy across space. These GRBs serve as cosmic messengers, providing clues about the most extreme processes occurring in the universe. But the story doesn't end with light alone. Alongside the electromagnetic radiation, the collision also sends out powerful gravitational waves, waves that spread through space and time, much like ripples on the surface of a pond. As these waves pass through space, they alter the distances between objects. Instruments on Earth can measure these slight changes, allowing scientists to observe and study events that occurred billions of years ago and are millions of light years away. The fusion of neutron stars is a violent process, and one of its most important outcomes is the creation of heavy elements like gold and platinum. These elements are forged in the intense conditions that arise from the merger. This process is known as rapid neutron capture, or the R process, which is responsible for the production of many of the heaviest elements in the universe. The energy released during the merger, including bursts of gamma radiation, helps to create these elements, which are then scattered back into space, enriching the surrounding environment. Over time, the ejected material cools and expands, eventually forming a nebula, a colorful and diffuse cloud of gas and dust that can serve as a nursery for new stars. This material, rich in heavy elements, contributes to the formation of future stars, planets, and even the building blocks of life itself. This combination of gravitational waves, electromagnetic radiation, and the creation of new elements provides scientists with a multi-messenger approach to understanding the universe. Each of these signals, whether it be the gravitational waves from the neutron star merger, the visible and gamma ray bursts from the kilonova, or the radio waves that linger in the aftermath, offers a unique perspective on the processes taking place. Together, they help to form a more complete picture of one of the most extreme and transformative events in the cosmos. The rapid response of observatories across the globe working in concert allows for an unprecedented level of detail in studying these collisions. When a neutron star collision occurs, the collaborative efforts of astronomers around the world provide the data necessary to explore these events from every conceivable angle. The information gathered from such events enhances our understanding not only of the mechanics behind these violent cosmic explosions, but also of the broader processes that shape the evolution of stars, galaxies, and even the formation of life. As we continue to refine our tools and techniques, the study of neutron star collisions promises to reveal even more about the forces that govern the universe. These cosmic events serve as natural laboratories for the study of the most fundamental forces in physics, providing answers to questions about the origin of elements, the behavior of matter under extreme conditions, and the nature of gravity itself. By looking at these cataclysmic events, we are peering deeper into the mysteries of the cosmos, uncovering the hidden mechanics behind the birth and death of stars, and perhaps even uncovering the secrets of our own existence. When two neutron stars collide, it marks one of the most awe-inspiring and cataclysmic events in the cosmos. These dense remnants of stars that have ended their lives in violent supernovae come together in a cosmic ballet, spinning around each other in a slow and ever-tightening spiral. As they draw closer, their immense gravitational pull begins to distort the very fabric of space-time itself, sending ripples through the universe. When they finally collide, the release of energy is unimaginable, outshining entire galaxies in the blink of an eye. This event, known as a neutron star merger, is not just a spectacular explosion. It represents an intricate cycle of destruction and creation. In the chaos of the collision, extraordinary temperatures and pressures arise, creating the perfect environment for a process called nucleosynthesis. During this event, atomic nuclei under the intense bombardment of neutrons undergo rapid transformations, creating heavy elements. The very elements that make up the gold in our jewelry, the platinum in our cars, and even the uranium used for energy are forged in this cataclysmic chaos. The energy unleashed in a neutron star merger is so vast that it can surpass the energy output of entire galaxies. These violent events are bright enough to be seen across vast cosmic distances and can even trigger the ignition of surrounding gas and dust. This, in turn, can spark the birth of new stars, giving rise to fresh cycles of star formation. The collision of neutron stars, therefore, is not only an event of destruction, it is one of creation. New stars, new elements, and, potentially, new planets and even life. This remarkable interaction between destruction and creation showcases the ever-evolving nature of the universe. Every neutron star merger enriches the surrounding cosmos with heavy elements that were once locked within the cores of ancient stars. These elements are scattered throughout space, becoming part of new stars, planets, and, eventually, life itself. The universe is a dynamic system where even the most violent events can lead to new beginnings, and the cycle of creation continues endlessly. The significance of these events extends far beyond the birth of new stars or the creation of heavy elements. Neutron star mergers also offer us a glimpse into the most fundamental forces of nature. They help scientists study the nature of gravity, understand the life cycles of stars, and investigate the origins of the elements that make up everything we know. The study of neutron star mergers thus offers a deeper understanding of the interconnectedness of the universe, how every star, every planet, and every element is part of an intricate cosmic dance that has been unfolding for billions of years. Moreover, the aftermath of such collisions sends gravitational waves rippling through the fabric of space-time. These waves, detected by observatories on Earth, offer us a unique way to study the most extreme environments in the universe. Gravitational waves provide critical insights into the nature of space, time, and the universe's most intense phenomena. By observing these waves, scientists can study not just the collisions themselves, but also the properties of neutron stars, black holes, and the very fabric of the universe. In addition to the creation of heavy elements, the energy released during these events ignites a process known as the rapid neutron capture process, our process. This process occurs under extreme conditions where neutrons are captured at an astonishing rate by atomic nuclei, creating elements much heavier than iron. These newly formed elements are ejected into space as the neutron stars merge, spreading throughout the cosmos and enriching the interstellar medium. This material, eventually incorporated into new stars, planets, and other celestial bodies, forms the building blocks of the next generation of cosmic structures. The importance of neutron star mergers is also evident in the way they shape the future of galaxies. The heavy elements produced during these collisions can influence the chemical composition of galaxies, affecting everything from star formation rates to the development of planets. These events, though rare, have a profound impact on the evolution of the universe, contributing to the complex tapestry of matter that we see today. Though neutron star mergers are exceedingly rare, when they do occur, they send shockwaves through space and time. They remind us of the astonishing forces at work in the universe and the interconnectedness of all things. These events are a testament to the complexity and dynamism of the cosmos, where moments of pure destruction give birth to the very elements that sustain life and form the foundation of new stars and planets. The collision of neutron stars, despite its rarity, is one of the most powerful and significant events in the universe. The aftermath of such a collision, an explosion brighter than anything we typically observe in the night sky, enriches the universe with essential elements and triggers new cycles of star formation. The universe's cycle of birth, death, and rebirth continues, all thanks to these extraordinary cosmic events. As these celestial objects spiral toward their inevitable merger, they remind us of the profound and interconnected nature of the cosmos, where even in the darkest moments of destruction, there lies the potential for the creation of new worlds and new beginnings. Ultimately, neutron star mergers embody the very essence of the universe's grand design. Through their destructive yet creative power, they play a crucial role in shaping the structure and composition of the cosmos, offering us new insights into the forces that govern the universe. And with every merger, we are reminded of the cyclical nature of the cosmos, where each ending is but the beginning of something new. Gravitational waves, those ripples in the fabric of space and time, remain one of the most fascinating and elusive phenomena observed by scientists. Though the exact number of neutron star collisions is still a mystery, many scientists believe these cosmic events happen more often than we can currently detect. The vastness of space, combined with the limitations of our observational capabilities, means that we only catch a fraction of these violent collisions. In 2017, however, a remarkable event, dubbed GW 708117, marked a breakthrough in our understanding. This was the first time scientists observed a gravitational wave signal originating from a neutron star merger. Not only did this event provide a direct observation of gravitational waves, but it also delivered electromagnetic signals across various wavelengths of light, detected right here within our very own Milky Way galaxy. Despite the excitement surrounding this discovery, it is essential to recognize that we don't know the exact frequency of neutron star collisions. Based on current simulations and observations of nearby galaxies, researchers estimate that such collisions could occur once every few thousand years within our galaxy. But even with this estimate, direct evidence remains elusive. Scientists study remnants from ancient supernovae and the current population of neutron stars to infer where such collisions might have recently taken place, even in the absence of direct observation. While we can't yet pinpoint each individual collision, we can still gather valuable information from the ongoing cosmic symphony of neutron stars, which allows us to explore these enigmatic events unfolding in our galactic neighborhood. The consequences of these catastrophic collisions extend far beyond their immediate surroundings. Neutron star mergers are believed to be the cosmic birthplace of some of the universe's heaviest elements, such as gold and platinum. In addition, these events generate gravitational waves that ripple outward, spreading across the cosmos like an unseen disturbance in the ocean of space-time. With the constant advancement of observational technology and enhanced detection strategies, we stand on the cusp of discovering more about these enigmatic cosmic phenomena, happening right under our noses, or perhaps more accurately, in the vast stretches of the universe around us. To predict and understand neutron star collisions, scientists rely on a combination of advanced computer simulations and observational data. At the heart of this study lies an understanding of the unique properties of neutron stars, the incredibly dense remnants left behind when a massive star undergoes a supernova explosion. The core that remains after such an explosion is so compact that a teaspoon of neutron star material could weigh as much as an entire mountain. This extreme density sets the stage for some of the most violent and energetic interactions in the universe. Simulating these collisions is no small feat. Scientists use highly detailed models that replicate the behavior of neutron stars, factoring in their masses, spins, and the distance between them. Using these simulations, researchers can model how two neutron stars, caught in each other's gravitational pull, gradually spiral toward each other over time. As they approach one another, the immense gravitational forces at play begin to distort the stars' shapes, creating enormous tidal forces capable of tearing them apart. These models, based on equations that describe the interactions of gravity and matter under extreme conditions, give scientists the tools to visualize the process of neutron-star mergers. While simulations provide valuable insight, real-world observations offer direct evidence of these collisions. In recent years, astronomers have detected gravitational waves emanating from actual neutron-star mergers, confirming many of the predictions made by simulations. By comparing these observations with the results of their simulations, scientists can refine their models, enhancing our understanding of the physics at play in these cataclysmic events. The combination of simulation and real-world data gives us a unique lens through which to explore the incredibly violent and energetic nature of neutron-star collisions. The consequences of such a collision, especially if it were to occur within proximity to our solar system, could be dire. Neutron stars are among the densest objects in the universe, and when two of these stars collide, they release unfathomable amounts of energy. This energy could manifest as powerful gamma-ray bursts, which are the most intense forms of light known to science. If one of these gamma-ray bursts were directed toward Earth, the consequences would be catastrophic. The burst could strip away Earth's atmosphere, leaving our planet exposed to the harsh vacuum of space and eliminating the very air that supports life. The radiation produced could also create high-energy particles that bombard the Earth, potentially damaging everything from electronic devices to the delicate biological systems that sustain life. In addition to gamma-ray bursts, a neutron-star merger also generates gravitational waves, ripples in space-time that spread outward from the event. While we currently have the tools to detect these waves, a nearby neutron-star collision could be so powerful that it might disrupt the orbits of planets in our solar system, throwing the delicate balance of our gravitational interactions into chaos. Such disruptions could lead to unpredictable consequences, from altering the paths of planets to causing shifts in the alignment of objects within the solar system. The fallout from a nearby neutron-star collision could also trigger intense stellar activity, influencing the environments of surrounding star systems. As these massive stars merge, they create elements like gold and platinum, enriching the cosmos with these precious materials. However, this process could also lead to additional cosmic events, further altering the balance of energy and matter in the surrounding region. Should such a collision occur near us, Earth would face multiple threats from intense radiation, gravitational disturbances, and a dramatic release of energy that could change our environment in unpredictable and catastrophic ways. Neutron stars, the remnants of massive stars that have gone supernova, are scattered across the universe, though not uniformly. These fascinating objects are most commonly found in regions where massive stars are born and die, areas of active star formation within galaxies. In our own Milky Way, neutron stars are primarily concentrated in the spiral arms, the regions where young, massive stars come into being. Since neutron stars are a product of specific stellar processes, their distribution reflects the life cycle of the stars that gave birth to them. Beyond our galaxy, neutron stars are present in other galaxies as well, often found in regions of active star formation. In some cases, neutron stars can also be found in globular clusters, which are spherical collections of stars orbiting galaxies. However, these objects can be quite elusive due to their small size and faint radiation. Many neutron stars go undetected unless they have companions, often pulling material from them, which can create bright X-ray emissions visible to our instruments. The distribution of neutron stars changes with age. Younger neutron stars, those born from recent supernovae, tend to remain close to the dense molecular clouds where they formed. Older neutron stars, however, can drift farther from their birthplace, traveling through the vast interstellar medium. As time passes, they become more scattered, moving alone or in smaller, more dispersed groups across the cosmos. Thus, neutron stars are primarily found in star-forming regions of galaxies, especially in the Milky Way, but their location and concentration change over time as they age and move through the cosmos. Each neutron star tells a story about the life cycle of stars and the dynamic nature of our universe. These remarkable and extreme objects offer a window into the fundamental workings of the universe. When a massive star runs out of nuclear fuel and undergoes a supernova explosion, what remains is a neutron star, a dense core that can have the mass of our sun compressed into a volume no larger than a city. If two of these neutron stars find themselves in a close orbit, they can eventually spiral inward and collide, releasing vast amounts of energy. This process is critical to understanding the creation of gravitational waves. As the two neutron stars orbit one another, they generate ripples in spacetime, similar to how a pebble dropped into a pond creates waves on the surface. As these stars draw closer, they lose energy, causing their orbits to decay and bringing them ever closer together, resulting in stronger and more detectable gravitational waves. The violent nature of these cosmic events continues to captivate us, providing both direct and indirect evidence of the ongoing interactions between the densest, most energetic objects in the universe. The merging of neutron stars not only illuminates the mysteries of gravity and space-time, but also provides us with a glimpse into the origins of some of the universe's heaviest elements. As our technology advances, we are poised to uncover even more about these dramatic celestial collisions that shape the fabric of our cosmos. When two neutron stars collide, the event releases an extraordinary burst of energy, one so immense that it exceeds the total energy output of the sun across its entire lifespan. This dramatic collision sends gravitational waves rippling across the cosmos, stretching and squeezing space itself as they travel through the universe. These waves, imperceptible to the naked eye, are detectable by sensitive instruments here on Earth, providing scientists with crucial insights into some of the most powerful and enigmatic phenomena in the universe. The detection of gravitational waves from neutron star mergers has unlocked an entirely new dimension in our understanding of the cosmos. It's as if a new window has opened, one that allows us to peer deeper into the mysteries of the universe than ever before. These waves carry with them not only information about the stars involved, but also about the processes that shape the universe itself, such as the formation of heavy elements. Elements like gold, platinum, and uranium, metals that are crucial to life as we know it, are forged in the heart of these violent collisions, formed under conditions that are impossible to replicate in laboratories on Earth. Every detection of gravitational waves brings us one step closer to understanding the underlying forces that govern the universe, revealing the profound connection between these cosmic events and the very fabric of space and time itself. The energy released in these catastrophic events, while brief in cosmic terms, is so immense that it reshapes our perception of the universe's power and complexity. As these waves spread, they stretch and distort the very space-time continuum, creating ripples that resonate across vast distances. Neutron stars, the remnants of supernova explosions, are incredibly dense and compact objects. After a massive star exhausts its nuclear fuel and undergoes a catastrophic collapse, what remains is a neutron star, a stellar remnant so dense that a single teaspoon of its material could weigh as much as Mount Everest. The force of gravity inside these stars is so intense that it compresses the core of the star into a sphere that may only be a few kilometers in diameter. Despite their small size, their mass is so great that the gravitational field surrounding them can influence objects light years away. Imagine for a moment the neutron star as a heavyweight boxer moving through a crowded ring. It moves with great force and, as it does, its immense gravity disturbs everything in its path. Nearby stars, gas clouds, and even entire galaxies feel the gravitational pull. These objects are bent off their course, their orbits altered, and their paths shaped by the overwhelming presence of the neutron star. It's as if the neutron star is conducting an invisible symphony, influencing the movements and interactions of everything in its vicinity. When a neutron star moves through a galaxy, it can create areas of high density, where stars are drawn together, sometimes triggering the formation of new stellar systems. The gravitational forces of neutron stars can cause surrounding gas and dust to accumulate and condense into disks around the star. Over time, these disks can collapse under their own gravity, leading to the birth of new stars in an intricate dance of cosmic creation. Furthermore, the interaction between the neutron star and the surrounding environment can produce breathtaking phenomena such as the emission of high-energy radiation. The intense heat generated by the material in these disks can result in brilliant X-ray emissions, which shine brightly across the universe, detectable by telescopes light years away. The collective influence of neutron stars in a galaxy can extend far beyond their immediate surroundings. These dense remnants of dead stars can shape the dynamics of entire galaxies, altering their structure and motion over time. When clustered together, groups of neutron stars can act as gravitational anchors, pulling on nearby stars and shaping the motions of other celestial bodies. Their presence can even have subtle, long-term effects on the overall evolution of the galaxy, influencing the birth and death of stars and the formation of new structures within the galactic expanse. Neutron stars are, in many ways, like cosmic magnets. Their immense gravitational pull acts on the fabric of space itself, guiding the movements of stars, initiating the formation of new stellar bodies, and influencing the overall structure of galaxies. Their existence serves as a stark reminder of the enormous forces at work in the universe, forces so powerful and so complex that they shape the very nature of space and time. These objects, though small in size, wield an unimaginable influence over the celestial realms they inhabit. At their core, neutron stars are the remnants of supernovae, the explosive deaths of massive stars that have exhausted their nuclear fuel. During these catastrophic events, the core of the star collapses under its own gravity, compressing matter to extraordinary densities. Protons and electrons combine to form neutrons, creating an object of unfathomable density and gravitational pull. The result is a neutron star, a dense, compact body that challenges our understanding of the laws of physics. Studying neutron stars is a way for scientists to gain a deeper understanding of the life cycle of stars and the evolution of the universe. Each neutron star is a relic of a star's explosive end, carrying with it a history of its progenitor. By analyzing the properties of these stars, such as their mass, age, and magnetic field, astronomers can reconstruct the history of the star from which the neutron star formed. This helps us better understand how stars live, evolve, and eventually meet their explosive end. Neutron stars, in this sense, serve as cosmic fossils, offering a glimpse into the past and shedding light on the broader processes of star formation and the chemical evolution of galaxies. Moreover, neutron stars provide a natural laboratory for testing extreme physics. The conditions inside a neutron star are unlike anything we can replicate here on Earth. The gravity, density, and pressures are so extreme that they offer a unique environment for testing theories of nuclear physics and gravity. For example, studying how matter behaves under these conditions can provide clues about how the fundamental forces of the universe interacted in the earliest moments after the Big Bang. Neutron stars, therefore, not only help us understand the evolution of stars, but also give us a window into the very forces that shaped the universe during its infancy. In these ways, neutron stars are far more than just remnants of dead stars. They are vital to understanding the universe itself. Through their study, we gain insights not only into the life cycle of stars, but also into the nature of space, time, and the fundamental forces that govern the cosmos. Each discovery about neutron stars opens up new possibilities for understanding the most extreme conditions of the universe and the remarkable phenomena that occur under them. Neutron stars, some of the most extraordinary and enigmatic objects in the cosmos, offer a window into the deepest workings of the universe. Born from the explosive demise of massive stars, these dense remnants are among the most extreme environments known to exist. With masses greater than our sun, but compacted into a sphere roughly the size of a city, neutron stars are not just cosmic oddities. They serve as natural laboratories for studying the very fabric of space, time, and fundamental physics. One of the most captivating phenomena associated with neutron stars is the powerful gravitational waves they produce, especially during events such as the collision of two neutron stars. When these stellar remnants crash together, they send out ripples across the fabric of space-time, waves that travel vast distances, carrying with them crucial information about the event itself. These gravitational waves allow astronomers to detect these cataclysmic events from billions of light years away. But their significance goes beyond just observing the collision itself. Each detection provides a rare glimpse into the properties of neutron stars and the intense forces that govern their behavior, helping to refine our understanding of the universe's underlying laws. In addition to providing insights into neutron stars, these collisions also hold essential clues about the rate of star formation across the universe. By studying the frequency and distribution of such events, scientists can gauge the pace at which stars are born and die in distant galaxies. More profoundly, these collisions illuminate the nature of the distances over which such catastrophic phenomena can occur, offering a deeper understanding of the scale and structure of the universe. But the significance of neutron stars extends beyond their role in cosmic observation. These objects are also vital players in the ongoing process of cosmic recycling. During explosive events, such as when neutron stars merge, they can forge heavy elements that are crucial for the formation of new stars, planets, and even life itself. Elements like gold, platinum, and uranium are thought to be created in these extreme environments and are dispersed throughout the galaxy. As these heavy elements spread across the cosmos, they contribute to the creation of new stellar systems and ultimately the birth of planets that may host life. By studying the processes at work in neutron star collisions, scientists can trace the origins of the very elements that make life possible, revealing the interconnectedness of cosmic events and biological existence. Neutron stars are, in a sense, time capsules. They preserve critical information about the evolution of the universe, offering a snapshot of its past while shedding light on its future. As astronomers study these celestial objects, they can piece together the grand narrative of the universe's life cycle. These stars provide insight into the birth, life, and death of stars, the mechanics of galaxy formation, and the dynamic processes that govern the cosmos. In this way, neutron stars offer a profound opportunity to explore the limits of physical laws and understand how the universe evolves over time. In addition to their role in revealing the cosmic story, neutron stars also act as natural testing grounds for Einstein's theory of general relativity. The intense gravitational fields around these stars create environments where the effects of gravity can be observed in extreme conditions, offering a unique opportunity to test the predictions of general relativity. For instance, in binary systems where a neutron star orbits another star, the gravitational influence of the neutron star warps spacetime. According to general relativity, this warping should affect the passage of time and the behavior of light in the region surrounding the neutron star. By observing the way light patterns change in the companion star, astronomers can test whether these predictions hold true under real-world conditions. One of the most dramatic tests of general relativity comes from the detection of gravitational waves. When two neutron stars collide or merge, the resulting event sends out ripples in spacetime that propagate across the universe. These waves carry information about the energy released during the collision, allowing scientists to study the event and verify Einstein's theories. The detection of such waves has provided compelling evidence that general relativity remains accurate, even in the most extreme conditions of gravity and spacetime curvature. Furthermore, neutron stars offer an invaluable opportunity to explore the deepest mysteries of the universe. They provide a platform for studying dark matter and dark energy, two of the most elusive and poorly understood components of the cosmos. The powerful gravitational fields of neutron stars allow scientists to test theories about the interaction between visible matter and dark matter, which is believed to make up a substantial portion of the universe. By analyzing the behavior of neutron stars and their interactions with surrounding matter, researchers can infer the properties of dark matter and gain new insights into its distribution and effects on the large-scale structure of the universe. Neutron stars also provide clues about the nature of dark energy, the mysterious force thought to be responsible for the accelerated expansion of the universe. When neutron stars merge, they release an enormous amount of energy, both in the form of electromagnetic radiation and gravitational waves. These events might be influenced by the behavior of dark matter or dark energy, and studying them can help scientists better understand how these forces shape the universe. As these mergers produce heavy elements, such as gold and platinum, They offer a direct link between the cosmic forces at play and the creation of the building blocks of life. The extreme density of neutron stars plays a crucial role in these investigations. A single cubic centimeter of neutron star material can weigh as much as an entire mountain on Earth. This incredible density creates conditions that are impossible to replicate in laboratories on our planet, making neutron stars essential for testing the limits of our understanding of physics. In these environments, mass and energy interact at their most extreme, offering a unique opportunity to explore fundamental questions about the universe, such as the behavior of matter and energy at the smallest scales. Ultimately, neutron stars represent some of the most fascinating objects in the universe. Through their extreme gravity, powerful emissions, and role in cosmic recycling, they provide critical insights into the structure and evolution of the cosmos. Their ability to serve as laboratories for testing general relativity, as well as their potential to reveal the mysteries of dark matter and dark energy, makes them indispensable to our quest for understanding the universe. Neutron stars are not just remnants of dead stars. They are the keys to unlocking some of the deepest secrets of the cosmos. Neutron stars represent some of the most fascinating and extreme objects in the universe, providing an unparalleled glimpse into the mysteries of fundamental physics and cosmic evolution. These compact remnants of massive stars, formed after a supernova explosion, are incredibly dense, containing a staggering amount of mass within a volume no larger than a city. However, despite their minuscule size, they are powerhouses of energy and gravitational influence, affecting everything around them with forces so extreme they challenge our understanding of the laws of physics. At the core of scientific curiosity lies the role of neutron stars in the study of dark energy, a mysterious force that is driving the accelerated expansion of the universe. Researchers hypothesize that these dense objects may hold clues to dark energy's elusive properties, particularly because they provide natural laboratories where we can study matter and energy under extreme conditions. By studying the unique behaviors of neutron stars, especially during high-energy interactions like their formation and merger, scientists hope to uncover the secrets of dark energy and dark matter, two of the universe's most elusive and fundamental components. As cosmic laboratories, neutron stars offer an invaluable opportunity to explore the nature of matter at its most extreme. The stability of neutron stars in the face of intense energy environments allows researchers to simulate conditions that would otherwise be impossible to recreate on Earth. The extreme pressure and temperature within these stars can push matter to states that challenge the limits of theoretical physics, offering a chance to test fundamental forces like gravity and nuclear interactions under conditions of intense stress. Understanding these forces is key to unlocking deeper insights into the universe's hidden contents and, potentially, its ultimate fate. Neutron stars are not just fascinating in terms of their own properties, they also play a pivotal role in shaping the universe around them. They are among the densest objects in the cosmos, their intense gravitational pull having profound effects on nearby stars, planets, and asteroids. When a neutron star comes close to another stellar body, its immense gravity begins to warp space-time, creating powerful tidal forces. These forces are so strong that they can deform and even tear apart nearby planets and asteroids. In the case of asteroids, the tidal stress can be so great that they are ripped apart, sending debris spiraling toward the neutron star, where it forms an accretion disk, a swirling vortex of gas and dust that heats up to extreme temperatures and emits intense radiation. This radiation, which can be far brighter than entire galaxies, provides critical insight into the dramatic processes taking place around these stellar remnants. Imagine the neutron star as a giant magnet, pulling everything within its reach toward it with a force far stronger than that of any typical star. The result is a host of energetic phenomena that are both beautiful and violent. The neutron star's powerful magnetic field generates beams of radiation from its poles, which sweep across the cosmos like a cosmic lighthouse. These beams, known as pulsars, can interact with objects in their path, heating them up and even bombarding them with high-energy particles. The radiation emitted from these interactions can illuminate entire regions of space, revealing the complex dynamics of celestial bodies that otherwise might remain hidden. Despite their extreme nature, neutron stars can also help astronomers detect their presence from vast distances. Since these stars are so dense, their gravitational influence on nearby objects is substantial, allowing scientists to detect them through indirect means. When a neutron star is paired with a companion star, its gravitational pull causes the companion to wobble or follow a specific orbit. By carefully studying the motion of this companion star, astronomers can infer the mass of the unseen object, which, when combined with the observed X-rays emitted from the accretion disk, confirms the presence of the neutron star. This clever combination of light observations and motion analysis allows scientists to detect neutron stars even in the vastness of space, where their presence might otherwise remain undetected. As neutron stars age, they can transform into pulsars, spinning rapidly and emitting regular pulses of radiation like a cosmic clock. These pulsars can serve as valuable tools for studying the structure and dynamics of galaxies. Their regular emissions help astronomers map out the distribution of mass within a galaxy, while also contributing to the overall luminosity and energy output of the galaxy. Over hundreds of millions of years, the influence of neutron stars extends far beyond their immediate surroundings, affecting the orbits of other stars and contributing to the formation of stellar structures like star clusters and spiral arms. In this way, even the remnants of dead stars can play a crucial role in shaping the broader structure of the universe. The collision of neutron stars is one of the most energetic events in the universe. When two of these dense objects collide, they release an enormous amount of energy, creating gravitational waves, ripples in the fabric of space-time that propagate outward across the cosmos. These gravitational waves carry crucial information about the collision, helping scientists understand the properties of neutron stars and the fundamental forces at play. Additionally, these cataclysmic events can create heavy elements like gold and platinum, which are then spread throughout the galaxy. These elements become part of the next generation of stars and planets, contributing to the ongoing cycle of stellar evolution. The interplay of gravitational forces between neutron stars and other objects within a galaxy is similarly profound. Just as the motion of a single ice skater on a rink can affect those around them, the gravitational pull of neutron stars can alter the orbits of nearby stars and celestial bodies. This delicate dance of gravitational forces creates a complex and ever-changing dynamic within galaxies, contributing to their evolution over vast stretches of time. Neutron stars, through their gravitational influence and the dispersal of heavy elements, play a critical role in the ongoing formation and transformation of galaxies. Within the heart of a neutron star lies an environment of unimaginable density. The core, composed primarily of neutrons, particles with no charge but an immense mass, exists under conditions so extreme that the nuclear forces binding these neutrons together are stretched to their limits. These forces, which are among the strongest in nature, prevent the neutrons from collapsing under the immense gravitational pressure trying to crush them into oblivion. The balance between gravity and the strong nuclear force at the core of neutron stars is a subject of intense study, as it holds the key to understanding not just the behavior of matter in such extreme conditions, but also the fundamental forces that govern the universe. Neutron stars, as remnants of once mighty stars, thus represent both the end of a star's life and the gateway to unlocking the deepest mysteries of the cosmos. From their role in the formation of heavy elements to their impact on the structure of galaxies, these tiny but powerful objects have far-reaching consequences for the universe. By studying their properties, behaviors, and interactions, scientists are slowly piecing together a more complete picture of the universe's most enigmatic components: dark matter, dark energy, and the very fabric of space-time itself. The study of neutron stars not only pushes the boundaries of our knowledge, but also offers a glimpse into the forces that have shaped the universe from its earliest moments to its ongoing evolution. In the heart of a neutron star, it is the strong nuclear force, particularly between the neutrons, that plays a pivotal role in maintaining the delicate balance of stability. The neutrons within this dense core are held together by the strong nuclear force, despite being packed into an incredibly confined space where the usual atomic structures begin to break down. These neutrons are packed together under the extreme pressure that occurs in the formation of the neutron star, which typically arises from the remnants of a star that has exploded in a supernova. As the star collapses under the immense gravitational forces, the pressure becomes so extreme that it overcomes the usual forces that would keep atoms intact. The core of the star is crushed under gravity so intensely that atomic nuclei collapse into a state dominated by neutrons. This extreme compression leads to the creation of a neutron star, and at the core, nuclear forces take charge. They counterbalance the force of gravity, which otherwise would collapse the star further into a black hole. This balance between the inward pull of gravity and the repulsive forces between neutrons that arise from the strong nuclear interaction forms a state of equilibrium that holds the star in a fragile yet resilient balance. Within this unique environment, the neutrons themselves can pair up, and under these extreme conditions, matter can exist in exotic states that are not found anywhere else in the universe. One such state is a superfluid phase, where neutrons can move without friction. This would further stabilize the neutron star, contributing to the remarkable properties that define it. The strong nuclear force thus acts as the backbone of the star's structure, ensuring that this compact object does not collapse under the strain of its own gravity. Without the power of this force, the star would be unable to maintain its form, inevitably collapsing into an even denser and more compact state. The conditions found in neutron stars are unlike anything else in the cosmos. These stars are some of the densest objects in the universe, exhibiting a unique combination of pressure and density that is nearly impossible to imagine. To understand the intensity of the environment within a neutron star, consider the remnants of a massive star that has exploded in a supernova. After the explosion, all that remains is a tiny, dense core that is only a few kilometers across. This core is so compressed that atoms can no longer hold their usual structure, breaking down into a soup of neutrons. The pressures inside a neutron star are unimaginable. They far exceed the pressures found in the center of Earth, where the weight of overlying layers of rock and metal compresses matter into a dense state. The pressure inside a neutron star is so extreme that if you were to take just a single cubic centimeter of its material, it would weigh as much as a mountain here on Earth. To put this into perspective, imagine a piece of material no bigger than a sugar cube. This tiny chunk would weigh more than Mount Everest itself. This overwhelming density and pressure are unparalleled in the universe. When compared to other cosmic entities, such as regular stars, gas giants like Jupiter, or even the dense cores of planets, the pressures inside a neutron star remain the most extreme. While stars like our Sun rely on nuclear fusion in their cores to generate energy and resist collapse, they never reach the kind of density that a neutron star does. Gas giants, which are massive in their own right, have much lower densities and much more moderate pressures in comparison. Neutron stars, with their superdense cores, create a cosmic phenomenon unlike anything else, where the normal laws of physics are stretched to their absolute limits. This extreme environment fosters extraordinary interactions between particles, pushing matter into new states and creating conditions that are unlike anything observed elsewhere in the universe. In the intense gravitational field of a neutron star, particles move at speeds approaching a significant fraction of the speed of light. This occurs because the immense gravity of the neutron star accelerates particles to relativistic speeds, meaning they move so fast that their mass increases as they approach the speed of light. The gravity of the neutron star distorts space-time, and as particles move closer to the star's surface, they experience a time dilation effect. From the perspective of an observer far away from the star, time seems to slow down for the particles as they approach the neutron star. This time dilation isn't just a curious phenomenon, it has real implications for how particles behave in the vicinity of a neutron star. As particles zip through the extreme gravitational field, they collide at incredibly high speeds, sometimes creating new particles in the process. This is similar to the high-energy reactions seen in particle accelerators, but instead of being artificially created, these collisions occur naturally. Such interactions offer a unique window into the fundamental forces that govern the universe and help scientists explore the forces of nature that operate in extreme environments. The environment around a neutron star serves as a natural laboratory for studying the behavior of matter under extreme conditions. It is a place where relativity, quantum mechanics, and nuclear physics come together to shape the way particles behave. These interactions reveal much about the fundamental structure of the universe and provide insights into the forces that govern matter and energy. One of the most fascinating aspects of neutron stars is their role as pulsars. A pulsar is a neutron star that emits beams of radiation from its magnetic poles as it spins. These beams of radiation sweep across space, much like the beam of a lighthouse, and if they happen to cross Earth's path, we detect them as regular pulses of electromagnetic radiation. This periodic emission gives pulsars their name, and the predictability of these pulses makes them incredibly useful to scientists. The precision of a pulsar's pulse is so exact that it can function like a cosmic clock. Scientists use these pulsars to measure time across vast cosmic distances, allowing them to test theories of gravity and explore the nature of space and time. Each new discovery about pulsars brings us closer to understanding the mysteries of the universe. The regularity of the pulses also gives us a deeper understanding of the life cycles of stars and how they evolve over time. Neutron stars, in their early stages, spin at incredibly high rates, often completing a full rotation in mere milliseconds. This rapid spin is a result of the conservation of angular momentum, a principle that explains how a rotating object in space will continue to spin at the same speed unless acted upon by an external force. Over time, however, neutron stars begin to slow down. This gradual decrease in spin rate happens because the neutron star loses energy as it emits radiation. As the star spins, it sends out powerful beams of electromagnetic radiation, which carry away the star's rotational energy. As a result, the neutron star begins to slow its rotation, eventually reaching a much slower spin rate over billions of years. The study of this slow-down process helps scientists understand the life cycle of neutron stars and the forces that drive the evolution of stars in general. Thus, a neutron star is not just a dense, compact remnant of a supernova. It is a cosmic marvel, constantly evolving and revealing the profound mysteries of the universe. Its extreme conditions and interactions with the fundamental forces of physics create a rich, complex environment that continues to captivate astronomers and physicists alike. Neutron stars, one of the universe's most fascinating and enigmatic objects, present an intricate dance between gravity, matter, and radiation. Formed from the remnants of massive stars that have exploded in a supernova event, neutron stars are born when a star's core collapses under its own gravity, creating a dense, highly compact object that defies our everyday understanding of matter and physics. These stars are not just compact, but they are incredibly dense, so much so that a single cubic centimeter of neutron star material could weigh more than an entire mountain on Earth. This extreme density results from a state of matter unlike anything we encounter on our home planet, where the atomic structure of elements breaks down under the crushing pressure. Protons and electrons merge to form neutrons, creating a neutron-dominated core. Despite their small size, often no larger than a city, neutron stars can pack more mass than the Sun itself into a volume smaller than a typical city block. In such an environment, the forces at play are so intense that they cause matter to behave in ways that challenge our most fundamental physical laws. The sheer density means that the normal atomic structure we are familiar with ceases to exist, replaced by a dense conglomerate of neutrons. As a result, the laws of physics, especially those relating to general relativity and quantum mechanics, start to bend and twist, making it incredibly difficult for scientists to predict the behavior of matter under these extreme conditions. This unique blend of phenomena makes neutron stars a paradox that even our most advanced theories cannot fully explain. The rotation of a neutron star is another extraordinary aspect. These remnants of supernovae are often in rapid motion, rotating several times per second and sometimes even faster. This rapid rotation, combined with the density of the material, creates a powerful magnetic field, far stronger than anything we experience here on Earth. The fast spinning action of the core essentially acts like a dynamo, generating electric currents from the highly charged particles within the star. These currents amplify the magnetic field to an intensity billions of times stronger than Earth's magnetic field. This amplification of the magnetic field, as a result of the rotation and the complex interactions inside the star, makes neutron stars some of the most magnetically intense objects in the known universe. Moreover, the magnetic fields of neutron stars are not static. They are dynamic and complex. Some neutron stars emit beams of radiation from their magnetic poles in a pattern akin to a lighthouse. As the star spins, these radiation beams sweep across space. If the beams happen to be directed toward Earth, we detect them as periodic flashes of radiation, known as pulsars. This phenomenon makes pulsars some of the most intriguing celestial objects, offering a glimpse into the extreme conditions of a neutron star. Pulsars are not the only magnetic marvels of neutron stars, though. In certain cases, these stars have magnetic fields so intense that they become magnetars, a special class of neutron stars with magnetic fields strong enough to cause extraordinary bursts of gamma rays. Magnetars produce violent outbursts of energy, releasing more radiation in a fraction of a second than the sun will emit over the course of its entire lifetime. These bursts of gamma rays can be so powerful that they affect the surrounding space environment, making magnetars among the most dangerous and energetic objects in the universe. Yet, despite their incredible energy, neutron stars are also subject to a gradual process of slowing down. If a neutron star is part of a binary system, meaning it orbits another star, it can lose angular momentum over time. This loss happens through the transfer of material or energy from the companion star, a process that contributes to the deceleration of the neutron star's rotation. As a neutron star loses angular momentum, its spin rate decreases, leading it to slow down over the course of millions of years. In extreme cases, this gradual loss of rotation can eventually cause the star to stop emitting detectable radiation signals, although this process varies significantly depending on the star's initial conditions and the characteristics of its environment. The evolution of a neutron star's spin rate is thus a complex, dynamic process, driven not only by energy loss through radiation, but also by interactions with companion stars. This interaction leads to a natural deceleration that can transform a once rapidly spinning object into a more slowly rotating one. However, even as neutron stars slow down, they remain among the most dynamic and captivating objects in the universe. Their magnetic properties, driven by ultra-dense matter and rapid rotation, shape not only the behavior of the stars themselves, but also influence their surrounding environments. These magnetic fields, with their incredible strength and variability, lead to a host of phenomena, from the characteristic pulse of radiation emitted by pulsars to the spectacular bursts of energy from magnetars. Neutron stars are truly unlike any other celestial body, and their extreme conditions force us to rethink our understanding of physics at the most fundamental levels. In many ways, neutron stars represent a frontier in astrophysical research. Their behavior stretches the limits of known physics, creating a zone where general relativity and quantum mechanics must be reconciled, and where the usual rules of matter and energy no longer apply in the same way. They are not just points of interest for theoretical physicists, they also have a profound impact on the structure and evolution of galaxies, influencing the dynamics of star systems and contributing to the production of heavy elements in supernova explosions. The complexity and the sheer strangeness of neutron stars make them one of the most exciting objects for both astronomers and physicists alike, offering insights into the forces that govern the universe on both the largest and smallest scales. As our ability to study these cosmic enigmas improves, we are likely to uncover even more surprising and unexpected truths about the nature of matter, energy, and the universe itself. The heart of a neutron star remains one of the most enigmatic frontiers in physics, where the realms of quantum mechanics and gravity collide with extraordinary intensity. This intersection, occurring under conditions that defy our current understanding, presents a profound challenge to physicists striving to unify the two pillars of modern physics, the theory of relativity and quantum theory. In these extreme environments, the laws governing the universe behave in ways that neither conventional theories nor the equations of general relativity can fully explain. This convergence of forces at the core of neutron stars serves as a crucible for new ideas with the potential to reveal some of the deepest secrets of the cosmos. Neutron stars are the remnants of massive stars that have reached the end of their lives. When these colossal stars explode in a supernova, they leave behind a core so dense that a single teaspoon of its material would weigh several billion tons on Earth. This compression of matter into a space roughly the size of a city transforms the star into one of the most fascinating objects in the universe. As these stars collapse, two extraordinary phenomena emerge: their rapid rotation and their powerful magnetic fields. The most captivating manifestation of this is the pulsar. Pulsars are a type of neutron star that emits a highly focused beam of radiation from its magnetic poles. Think of them as cosmic lighthouses sweeping across the cosmos with each rotation. As the neutron star spins, its beams flash in and out, creating a regular pulse pattern observable from Earth. These pulses are more than just mesmerizing. They also serve as a highly precise cosmic clock. Some pulsars rotate so rapidly that they complete multiple rotations each second, with their regular flashes providing scientists with a reliable measure of time in the vast emptiness of space. The discovery of these pulsating signals marked a significant milestone in astrophysics, leading to the development of cutting-edge observational tools. The sensitivity of modern radio telescopes capable of detecting the faintest signals from the depths of space owes much of its progress to the study of pulsars. The technology required to capture and analyze these signals, precise antennas, receivers, and sophisticated data processing algorithms, has paved the way for more advanced methods of studying distant celestial bodies. However, pulsars are not the only mystery that neutron stars hold. Magnetars, a particularly rare subclass of neutron stars, feature magnetic fields far stronger than those found in ordinary neutron stars. These incredibly intense magnetic fields can trigger violent bursts of energy in the form of X-rays and gamma rays. When a magnetar's magnetic field reconfigures itself, the release of energy can briefly light up its surroundings in an extraordinary display. This phenomenon serves as a reminder of the ever-changing and chaotic nature of the universe, as the delicate balance of forces in a magnetar can lead to such immense releases of energy. Both pulsars and magnetars demonstrate how the interplay between rotation and magnetism in neutron stars results in some of the most extreme and fascinating phenomena in nature. These stellar objects offer scientists a glimpse into the universe's most extreme conditions, highlighting the complex behavior of matter and energy at their most fundamental levels. Their study provides valuable insights not only into astrophysics, but also into the very nature of space and time, challenging existing theories and suggesting new paths for exploration. As scientists continue to probe the depths of these celestial objects, they uncover more about the fundamental forces that govern the universe. The discovery of neutron stars has, for example, been instrumental in advancing the field of high-energy astrophysics. The development of satellite-based telescopes and X-ray observatories has revolutionized the way we observe and study high-energy events in space. These innovations have not only deepened our understanding of neutron stars, but also provided valuable tools for studying other energetic phenomena in the universe, such as supernova and black holes. Beyond the immediate benefits for astronomy, the study of neutron stars has also catalyzed advancements in technology. The analysis of the data gathered from these objects requires vast amounts of computational power, leading to the development of faster and more efficient processing systems. Many of these innovations have found applications in other fields, including medical imaging and artificial intelligence. In this way, the quest to understand the neutron star has had far-reaching implications, fostering technological advancements that have changed our lives in ways both seen and unseen. Moreover, neutron stars provide a natural laboratory for testing the laws of physics under the most extreme conditions. The intense gravitational fields produced by these stars are so powerful that they challenge our current understanding of gravity, potentially offering insights into the very fabric of space-time. In fact, neutron stars could hold the key to a new theory of gravity that might go beyond Einstein's general theory of relativity. By studying how neutron stars warp the space around them, physicists could make profound discoveries that reshape our understanding of how the universe operates. The conditions within a neutron star are so extreme that they push matter to states that cannot be recreated on Earth. The pressure inside these stars is so immense that it forces matter into exotic forms. These exotic states could unlock new insights into the behavior of particles like neutrons, which normally exist in stable configurations. By studying how matter behaves under such extreme conditions, scientists hope to better understand the early universe, where similar densities and pressures were present. The knowledge gained could revolutionize material science and provide clues about the origins of the cosmos. Additionally, neutron stars are responsible for producing gravitational waves, ripples in the fabric of space-time that travel outward when the stars collide. The detection of these waves represents a monumental breakthrough, offering a completely new way to observe the universe. Unlike traditional telescopes, which rely on light to reveal cosmic events, gravitational wave detectors can sense these subtle distortions in space-time caused by catastrophic events like neutron star collisions. By analyzing these waves, scientists can gain insights into the properties of matter and energy under the most extreme conditions, as well as learn about other cosmic phenomena, including the formation of black holes. In the search to understand neutron stars, we are not only pushing the limits of our knowledge about the universe, but also opening new avenues of scientific discovery. With each breakthrough, we inch closer to unraveling the mysteries of the cosmos, gaining a deeper understanding of the fundamental forces that govern the universe. As our ability to observe and analyze the extreme environments within these stellar remnants continues to grow, so too does our capacity to explore the far reaches of space, with new technologies helping us peer further into the universe than ever before. The study of neutron stars is not just about understanding the past or present. It is about unlocking the future, revealing the deeper workings of the universe, and advancing technology in ways that continue to shape our world. The study of pulsars, rotating neutron stars that emit regular beams of radiation, offers an unparalleled opportunity to test and refine our understanding of some of the most fundamental aspects of physics. These enigmatic celestial objects not only provide insights into Einstein's theories of relativity, but also offer an avenue for exploring the mysteries of extreme matter, gravitational waves, and cosmology. Pulsars, in particular, serve as cosmic lighthouses, emitting periodic signals that can be used to make highly precise measurements across vast distances of space, effectively allowing scientists to gauge the very fabric of the universe with remarkable accuracy. Neutron stars, which arise from the explosive death of massive stars and supernova, represent some of the densest and most extreme objects known to science. They are the remnants of stars that have collapsed under their own gravitational pull, leaving behind a core of matter so tightly packed that a cube the size of a sugar cube would weigh as much as a mountain here on Earth. This extraordinary density results in gravitational and magnetic fields that are far beyond anything we encounter on our planet. The strength of these fields pushes the boundaries of physics and challenges our understanding of fundamental forces. Because neutron stars are so incredibly dense, their study requires cutting-edge technology. Detecting and observing these objects demands advanced telescopes capable of sensing high-energy radiation, including X-rays and gamma rays, that are emitted from the neutron stars' surfaces. This has driven the development of increasingly sensitive astronomical instruments. For example, the study of pulsars, which are rapidly rotating neutron stars that emit beams of radiation, has spurred the creation of instruments capable of detecting even the faintest of signals. These signals, often weaker than the most distant galaxies, are picked up by powerful telescopes and used to calculate incredibly precise measurements. Pulsars themselves serve a dual role in the scientific community. Not only do they help improve the precision of astronomical observations, but they also act as cosmic clocks, offering a regular and reliable rhythm that can be used to develop ultra-precise timing systems. This, in turn, enables scientists to make increasingly accurate measurements across vast distances in space. Moreover, the extreme conditions found around neutron stars challenge our existing understanding of fundamental physics, particularly in terms of gravity and the behavior of matter at incredibly high densities. The need for specialized tools to study neutron stars has driven innovations in a variety of scientific fields, far beyond just astronomy. For instance, the study of pulsars and neutron stars has led to improvements in timing systems, which are critical in various scientific and engineering disciplines, from communications to GPS technology. Even more surprising, some of the advancements in astronomical instruments have found applications in fields like medical imaging and material science. This is a perfect example of how progress in one area of science can have far-reaching impacts across other domains, sometimes in unexpected ways. In addition to conventional telescopes, which are crucial for visualizing neutron stars in different forms of light, researchers also employ gravitational wave detectors. When neutron stars collide, they send out ripples in the fabric of space-time, known as gravitational waves, that can be detected by highly sensitive instruments on Earth. These waves provide a wealth of information about neutron stars, including their masses, spins, and even the dynamics of their merger events. These collisions often produce bursts of gamma rays, adding another layer to our understanding of these extreme cosmic phenomena. X-ray observatories positioned above the Earth's atmosphere are also vital tools for studying neutron stars. These observatories detect the high-energy emissions resulting from the intense heat and pressure present on the surface of a neutron star. By analyzing these emissions, scientists can determine not only the star's temperature and composition, but also gain insight into the processes that occur during its formation and subsequent evolution. These observations play a crucial role in refining our understanding of how neutron stars evolve and how they interact with the surrounding space. To complement observational data, computer simulations have become an indispensable tool in the study of neutron stars. These simulations can recreate the extreme conditions inside neutron stars, providing a theoretical framework for understanding their internal behaviors and structures. By comparing the predictions from these simulations with actual observational data, scientists can refine their models and improve their understanding of the fundamental physics that govern these incredibly dense objects. The combined use of these advanced techniques, telescopes, gravitational wave detectors, X-ray observatories, and simulations, forms a comprehensive toolkit for studying neutron stars. Each method contributes a unique piece to the puzzle, allowing researchers to slowly unravel the mysteries surrounding these dense cosmic objects. This intricate blend of observational and computational technologies continues to reveal the secrets held by the universe's most extreme stars, challenging our understanding of everything from gravity to the very nature of matter itself. At their core, neutron stars serve as natural laboratories for testing fundamental theories of physics. The conditions inside these objects are so extreme that they provide an unparalleled environment for studying the behavior of matter under stress, far beyond anything we encounter in our everyday lives. Neutron stars are a playground for scientists looking to explore the nature of atomic nuclei, as their cores are primarily composed of neutrons, particles that are usually found within the nuclei of atoms, but are packed into these stars at densities that dwarf anything seen on Earth. The immense gravitational fields of neutron stars also produce strong gravitational waves, which are ripples in space-time that stretch and compress the fabric of the universe. These waves are not only a product of neutron star mergers, but can also be generated by the intense gravitational fields surrounding individual stars. By studying these waves, scientists are able to test the limits of general relativity and gain new insights into the structure of space-time itself. Moreover, the study of neutron stars contributes directly to our understanding of nuclear physics. The matter inside these stars is compressed to such extreme densities that it is thought to be in a state of matter not seen anywhere else in the universe. This state could potentially reveal new forms of matter beyond the well-known protons, neutrons, and electrons that make up ordinary matter. The behaviors of these dense particles under extreme pressure and temperature conditions could offer new perspectives on the fundamental forces that govern the universe. In conclusion, the study of neutron stars and pulsars offers far more than just a glimpse into the life cycles of massive stars. It opens up a window into the fundamental workings of the universe, providing insight into some of the most extreme conditions found anywhere in nature. Whether it's refining our understanding of gravity, probing the mysteries of nuclear matter, or enhancing the development of cutting-edge technologies, the research into neutron stars continues to push the boundaries of human knowledge, prompting us to rethink what we know about the universe and inspiring the next generation of scientific inquiry. Neutron stars, the enigmatic remnants of massive stars that have undergone catastrophic supernova explosions, provide a wealth of information about the universe. These objects, despite their small size, are filled with information that can shed light on the evolution of stars, the mysteries of gravity, and the very nature of space-time. As researchers delve deeper into understanding how neutron stars behave over time, they uncover secrets not only about the stellar life cycle, but also about the forces that govern the cosmos. From the birth of these extraordinary objects to their eventual fate, neutron stars offer an extraordinary opportunity to explore the most extreme conditions in the universe. When a massive star reaches the end of its life cycle, it exhausts its nuclear fuel, leading to a dramatic collapse. This collapse causes the core to become incredibly dense, and the result is a neutron star, an object that, despite having a mass greater than that of the Sun, is only about the size of a city. The sheer density of neutron stars is difficult to comprehend, as a teaspoon of neutron star material would weigh several billion tons on Earth. In the immediate aftermath of their formation, neutron stars are intensely hot, with temperatures reaching millions of degrees. However, this heat gradually dissipates over millions of years as the neutron star cools down, emitting thermal radiation in the process. As it cools, the neutron star becomes less luminous, eventually fading from view, but not before it leaves behind a trail of vital information that astronomers use to piece together the complex story of stellar evolution. In addition to their temperature and luminosity, neutron stars are distinguished by their incredibly strong magnetic fields, which are billions of times stronger than Earth's magnetic field. As the star cools, these magnetic fields continue to influence their surroundings, often leading to the emission of beams of radiation. These beams are focused in such a way that they create a lighthouse effect, with the beams sweeping across space as the neutron star spins rapidly. This effect can result in the emission of regular pulses of energy, which can be detected by telescopes here on Earth. Over time, the rotation of neutron stars may gradually slow down due to the loss of energy, but in some cases, their rotation rate can fluctuate due to interactions with surrounding material, particularly if the neutron star is part of a binary system with a companion star. In such systems, the neutron star can siphon material from its partner, adding mass and altering its evolution. If enough mass is accumulated, the neutron star may reach a critical threshold that causes it to collapse into a black hole, marking the end of its life. The ultimate fate of a neutron star depends largely on its mass and its environment. For most neutron stars, the gradual loss of energy and the cooling process will lead to a point where they become less detectable, eventually transforming into what scientists call a black dwarf, a cold, inert remnant. However, the universe is not yet old enough for any neutron stars to have reached this stage. In the case of neutron stars in binary systems, the interaction with their companion can lead to a dramatic transformation. As the neutron star siphons material from its companion, it can reignite, leading to another supernova explosion. In some cases, this explosion can be powerful enough to trigger a black hole formation, adding another layer of complexity to the life cycle of these extraordinary objects. Neutron stars, through their extraordinary characteristics and their interactions with other celestial bodies, provide key insights into the evolution of the universe itself. In the early stages of the universe, just moments after the Big Bang, the cosmos was filled with a hot, dense mixture of energy and elementary particles. As the universe expanded and cooled, these particles began to combine, forming simple elements like hydrogen and helium. Over millions of years, clouds of gas collapsed under their own gravity, giving rise to the first stars. These early stars were massive and burned through their fuel rapidly. Once their nuclear fuel was exhausted, the core of the star collapsed, resulting in a supernova explosion. If the remaining core was massive enough, it could collapse further into a neutron star, an object defined by extreme density and unique physical properties. Neutron stars are not just fascinating remnants of dead stars. They also play a crucial role in the formation of the elements that make up our universe. The extreme conditions inside neutron stars are believed to be sites where elements heavier than iron, such as gold and uranium, can form. These elements are then scattered into space during supernova explosions or when neutron stars interact with other celestial objects. This process contributes to the chemical enrichment of the universe, playing a crucial role in the formation of planets, asteroids, and even life itself. The heavy elements created in neutron stars are essential for the development of complex chemistry, which eventually leads to the formation of the planets and stars we see today. As we continue to study neutron stars, we gain a deeper understanding of the forces that shape the universe. These objects serve as natural laboratories for extreme physics, testing the boundaries of our understanding of gravity, space-time, and the fundamental laws of nature. In particular, the study of neutron stars allows scientists to probe the limits of general relativity, a theory that describes how gravity operates on large scales. The intense gravitational fields of neutron stars test the predictions of this theory in ways that cannot be replicated on Earth. By observing the behavior of neutron stars, astronomers are able to refine our understanding of the laws that govern the universe. The study of neutron stars also provides insights into the nature of space-time itself. The extreme density of these objects distorts space-time to such an extent that the fabric of the universe is bent and warped. This warping of space-time can have profound effects on the surrounding space, influencing the motion of nearby objects and the behavior of light. Neutron stars are thus not only laboratories for extreme physics, but also gateways to understanding the very nature of the universe. In the grand timeline of the cosmos, neutron stars are both of a violent past and harbingers of the future. They represent a critical stage in the life cycle of stars, and their study offers valuable clues about the processes that drive the evolution of the universe. From the formation of the first stars to the eventual death of those stars as black holes, neutron stars are an essential piece of the cosmic puzzle. Their study provides a window into the forces that shape the universe, from the smallest subatomic particles to the grandest cosmic structures. And as the universe continues to evolve, these extraordinary objects will continue to shed light on the mysteries of the cosmos, offering new opportunities for discovery and understanding. Ultimately, neutron stars are not just remnants of the past. They are crucial players in the ongoing story of the universe's evolution. Through the study of these remarkable objects, scientists continue to uncover the secrets of the universe, from the formation of the first stars to the creation of heavy elements and the final fate of massive stars. Neutron stars, with their extreme conditions and unique properties, remain one of the most fascinating and important subjects of study in modern astronomy. Their contribution to our understanding of the universe is invaluable, offering a glimpse into the processes that shape the cosmos and providing clues about the future of the universe itself. A neutron star is one of the most remarkable and enigmatic remnants left behind after a massive star reaches the end of its life in a violent supernova explosion. When a massive star has exhausted its nuclear fuel and can no longer support its own core against the immense force of gravity, it collapses in on itself. This collapse results in an incredibly dense object composed mainly of neutrons, particles that are created when protons and electrons combine under extreme conditions. The neutron star is born in this chaotic process, and despite its small size, it is packed with an immense amount of mass. The resulting neutron star is often no larger than a city, but it contains more mass than our entire sun. This incredible density is a result of the collapse of the star's core, compressing matter to such an extent that the forces of gravity and the pressure from the neutrons themselves reach an equilibrium. In these extreme conditions, the star remains stable, resisting further collapse and preventing it from transforming into a black hole for billions of years. However, the stability of a neutron star is not a guarantee. While a neutron star can endure for billions of years in a seemingly stable state, it is subject to a variety of cosmic influences that can change its fate. One of the primary factors that can alter the star's stability is the accumulation of additional mass. If the neutron star is part of a binary system, it may interact with a companion star, drawing in material from its surroundings. This material, often in the form of gas or stellar debris, can gradually add to the star's mass, pushing it closer to the critical limit where it can no longer resist the force of gravity. If the neutron star gathers enough mass, it may eventually collapse into a black hole. Alternatively, neutron stars can undergo transformations due to their gradual cooling over time. As a neutron star ages, it continues to radiate energy into space, causing its temperature to drop. This cooling process is not instantaneous. It unfolds over vast cosmic timescales, often taking millions or even billions of years. As the star cools, its internal structure may undergo changes. The neutrons themselves may enter new states, such as the formation of superfluid phases, where matter behaves in ways that are beyond our everyday experience. These changes can have profound effects on the star's behavior and stability, potentially altering the state of matter inside the star in ways that are not yet fully understood. The fascinating nature of neutron stars extends beyond their extreme conditions. Their formation is a critical part of the life cycle of stars, marking the death of a massive star and the creation of one of the most extreme objects in the universe. The study of neutron stars provides valuable insights into the explosive processes that occur during the death of massive stars. When a massive star explodes in a supernova, it expels much of its outer material into space. This material, which can include elements such as carbon, oxygen, and iron, enriches the interstellar medium, seeding future generations of stars and planets with the raw materials necessary for life. These heavy elements are essential building blocks for the formation of new stars, planets, and potentially life itself. As neutron stars form, they also contribute to the ongoing cycle of matter in the universe, scattering these elements into space and creating a cosmic recycling process. The death of a star does not mark the end of the material it once contained. Instead, it marks the beginning of a new phase in the universe's ongoing process of birth and rebirth. Neutron stars serve as markers of stellar evolution, pointing to the incredible transformations that occur as stars live, die, and give birth to new forms of matter. Beyond their role in cosmic recycling, neutron stars also play a pivotal role in advancing our understanding of the universe's most extreme physics. The study of these stars helps scientists to probe the very nature of matter under the most intense pressures and magnetic fields. Neutron stars are not just remnants of dead stars. They are laboratories for testing the limits of physics. The forces within a neutron star are so powerful that they lead to unique phenomena such as intense magnetic fields and rapid rotation, some of which defy conventional understanding. When scientists observe neutron stars, particularly those that emit beams of radiation, known as pulsars, they are given a glimpse into the incredible processes at play in the collapse of massive stars. Pulsars are neutron stars that emit regular pulses of radiation due to their rapid rotation and intense magnetic fields. These pulses can be detected across vast distances, allowing scientists to study the neutron star's behavior in real time. The data gathered from these observations can provide crucial insights into the physical processes that govern the collapse of stars, the formation of neutron stars, and the extreme environments within them. However, understanding the internal structure of a neutron star remains one of the most significant challenges for scientists. The pressure and density inside a neutron star are beyond anything we can replicate on Earth. The gravitational pull is so intense that a single spoonful of neutron star material would weigh more than an entire mountain. This state of matter, where neutrons are packed so closely together, results in exotic forms of matter that cannot be easily observed or understood. Neutrons behave in ways that are not fully explained by conventional physics, and under such extreme conditions, they can form superfluid phases or pair up in ways that defy the typical behavior of particles. The mystery surrounding the interior of a neutron star is compounded by the fact that it is almost impossible to simulate these conditions in a laboratory setting. The densities and pressures inside a neutron star are so extreme that current technology cannot recreate them. Yet, by studying the observable properties of neutron stars, such as their magnetic fields, rotation rates, and emitted radiation, scientists are gradually piecing together a picture of the strange and exotic physics at work within these compact objects. In conclusion, neutron stars are among the most extraordinary objects in the universe. Born from the violent death of a massive star, they embody the dramatic transformation of matter under extreme conditions. They are not only remnants of a star's life cycle, but also essential players in the cosmic recycling process. Through their study, scientists can learn more about the fundamental forces of nature, the life and death of stars, and the very fabric of the universe itself. Neutron stars may be small, but their importance in the grand scheme of the cosmos cannot be overstated. They are windows into the most extreme environments in the universe, providing insights that challenge our understanding of the physical world and our place in the cosmos. Neutron stars are among the most enigmatic objects in the cosmos, captivating the minds of astrophysicists worldwide. These stellar remnants are born from the explosive deaths of massive stars collapsing under their own gravity into incredibly compact, dense spheres composed mostly of neutrons. However, despite the remarkable advances in both theoretical astrophysics and observational technology, the exact nature of these cosmic objects remains largely shrouded in mystery. Neutron stars are incredibly dense, often possessing a mass greater than that of the Sun, but confined to a diameter roughly the size of a city. This immense density leads to a host of unique characteristics that make studying them both challenging and intriguing. Their surfaces emit most of their energy in the form of X-rays and gravitational waves, which require sophisticated and advanced technology to detect and analyze. Unlike typical stars, which radiate light that can easily be detected from vast distances, neutron stars have a much smaller surface area from which to emit detectable radiation. Their weak emission signals make them difficult to observe, especially if they are not part of a binary system or aligned in such a way that their radiation beams can be detected by telescopes on Earth. Moreover, the techniques that scientists use to study neutron stars have their own set of limitations. The most common approach involves observing how these stars interact with their surroundings. For instance, researchers analyze the behavior of nearby matter, as well as the way neutron stars influence the space around them. However, this observational method cannot provide a complete picture of what lies beneath the thick and incredibly strong crust of a neutron star. This crust, while theoretically understood, remains an elusive barrier to fully comprehending the internal composition of these cosmic objects. One of the most pressing mysteries that scientists continue to explore is the internal structure of neutron stars. These celestial bodies are composed primarily of neutrons, but the exact composition of their cores remains a topic of heated debate. Are they entirely made up of neutrons, or do they also harbor exotic particles such as hyperons or even forms of quark matter? Unraveling the nature of the core could yield answers to fundamental questions about matter itself, including how it behaves under extreme conditions. It may also provide new insights into the forces that govern the behavior of the universe at its most fundamental level. The environment within a neutron star is unlike anything that can be replicated on Earth. The conditions inside these stars are so extreme, featuring immense gravitational forces, ultra-high temperatures, and unparalleled densities, that the standard laws of physics as we know them seem to break down. This has led scientists to probe deeper into the behavior of matter under these intense pressures, hoping to uncover new states of matter and perhaps even materials with extraordinary properties. The study of these phenomena could provide breakthroughs in fields like material science, as the materials formed under such extreme conditions might offer applications that are unimaginable in everyday life. In addition to their unique internal structure, neutron stars are also known for their role in the creation of gravitational waves. These waves, ripples in space-time caused by massive objects moving through it, can be detected here on Earth when neutron stars collide or merge. These cosmic events carry valuable information that could offer crucial insights into the nature of the universe. However, much about these mergers remains mysterious. For example, scientists are still unsure about the exact processes that occur during such collisions, particularly the mechanisms behind the violent explosions that result. These explosions are not only spectacular, but are thought to play a vital role in the creation of heavy elements like gold and platinum, which are dispersed throughout the universe during these cataclysmic events. The study of neutron stars also touches on the broader question of their evolution and lifespan. How quickly do neutron stars lose energy? How do they evolve over time, and what factors contribute to their eventual demise? These questions remain at the forefront of research into the life cycles of stars, offering critical insights into the fate of massive stars and their eventual transformation into dense remnants. By investigating these aspects, scientists aim to better understand the ultimate fate of stars in our universe and the processes that govern their birth, life, and death. In addition to these direct areas of study, neutron stars provide a window into the broader mysteries of the universe. As researchers push the boundaries of theoretical models and computational simulations, they are beginning to see glimpses of a more complete picture. Theoretical work is currently at the intersection of quantum mechanics and general relativity, with scientists attempting to reconcile these two fundamental theories. The combination of these fields of physics is crucial to understanding how neutron stars behave, especially given the extreme environments in which they exist. However, unifying these theories has proven to be one of the most difficult challenges in modern science. One of the more daunting aspects of modeling neutron stars is the uncertainty surrounding the properties of the nuclear matter within them. In these stars, the matter is subjected to pressures and temperatures so extreme that it cannot be replicated in terrestrial laboratories. Theoreticians use models that rely on equations to describe how neutrons interact under these conditions. But many of these equations remain untested due to the lack of experimental data. As a result, various models make different predictions about neutron star behavior, such as their internal structure, their cooling rates, and the potential formation of exotic states of matter. To piece together a more complete understanding of neutron stars, scientists combine theoretical models with observations from various sources. Pulsar data, for example, provides valuable information about rapidly spinning neutron stars that emit beams of radiation, sweeping across Earth like a cosmic lighthouse. Additionally, the detection of gravitational waves from neutron star mergers offers crucial insights into these objects' behavior, helping scientists refine their models. Each new discovery brings researchers closer to uncovering the many mysteries that remain, gradually revealing the truth about these astonishing objects. As challenging as it may be, the quest to understand neutron stars is one of the most exciting frontiers in astrophysics. These celestial bodies represent a unique opportunity to test the limits of our knowledge about the universe. The interplay of extreme densities, high magnetic fields, and intense gravitational forces creates a natural laboratory for studying the laws of physics in ways that are otherwise impossible. Neutron stars may hold the key to unlocking some of the deepest secrets of the cosmos, and their study is likely to continue to push the boundaries of science for years to come. As researchers delve deeper into the mysteries of neutron stars, they not only aim to unlock the secrets of these fascinating objects, but also hope to expand our understanding of the universe itself. The discoveries made along the way will undoubtedly have implications for fields beyond astrophysics, offering new insights into the nature of matter, the fabric of space-time, and the fundamental forces that govern the cosmos. The universe, vast and seemingly infinite, presents a multitude of challenges for scientists studying its many hidden phenomena. Among the most elusive objects are neutron stars, remnants of massive stars that have collapsed under their own gravity. These stellar remnants, although extremely dense and powerful, remain a mystery for a number of reasons. Their detection from Earth is an incredibly complex task, due in part to the sheer distance between us and these objects, as well as the extreme conditions of space that affect the signals we receive. The immense size of the cosmos itself plays a significant role in the difficulty of detecting neutron stars. These stars are located light years away, often so far that their emissions become nearly undetectable by the time they reach our planet. Even when neutron stars emit radiation, the signals can be weakened as they travel across vast stretches of space, making them too faint for even our most advanced instruments to capture. In addition to the sheer distance, space is far from empty. It is filled with interstellar dust and gas that can obstruct our view, scattering and absorbing light as it passes through. These particles can hide neutron stars from our detection systems, making it even more difficult to study them. Another complicating factor lies in the nature of our detection technology. While modern telescopes and instruments can observe a range of wavelengths from visible light to X-rays, types of radiation are not always detectable by all technologies. Neutron stars, depending on their nature and behavior, might not emit the kinds of radiation that our equipment is designed to detect. As a result, some neutron stars may remain invisible to us, evading the grasp of our current technology and understanding. This combination of vast distances, cosmic interference, and technological limitations means that despite our advancements, some neutron stars remain elusive, hiding in the far reaches of space. Neutron stars themselves are extraordinary objects, posing unique challenges for astronomers due to their extreme physical properties. These objects, typically no larger than a city in diameter, contain more mass than our Sun. Their density is so immense that the matter inside them is compressed to unimaginable extremes. The gravitational and magnetic fields surrounding these stars are so intense that they can warp light itself, further complicating efforts to observe them. Traditional methods of observing objects in space using visible light or even radio waves are often ineffective in studying neutron stars. The intense gravitational and magnetic forces can bend and distort these signals, making it even harder to detect these celestial objects. To overcome these challenges, scientists have developed innovative techniques and tools to study neutron stars. One of the most significant advancements in this area has been the use of radio telescopes. Neutron stars, particularly pulsars, emit beams of radio waves as they rotate. These beams sweep across the sky like a lighthouse beacon, and by observing them, scientists can gather data about the star's rotation speed, magnetic fields, and other characteristics. This technique has provided valuable insight into the behavior of neutron stars and the extreme conditions that exist within them. In addition to radio telescopes, X-ray telescopes have been instrumental in studying neutron stars. These stars often produce X-rays when material from a companion star is accreted onto their surface. The process generates immense heat, causing the material to emit X-rays that can be detected by space-based observatories like NASA's Chandra X-ray Observatory. Unlike radio waves, which can penetrate the Earth's atmosphere, X-rays are absorbed by the atmosphere, making ground-based observations ineffective. Space-based observatories are crucial in overcoming this barrier, allowing us to explore the surface temperature and magnetic properties of neutron stars in greater detail. Gravitational wave detection has also emerged as a powerful tool for studying neutron stars. When two neutron stars collide, they produce ripples in the fabric of space-time, known as gravitational waves. These waves carry vast amounts of information about the merging process and the behavior of the stars themselves. Projects like LIGO, Laser Interferometer Gravitational Wave Observatory, have successfully detected these waves, offering an entirely new way to observe the universe and gain insight into the processes at work in neutron stars. By combining data from multiple wavelengths, radio, X-ray, and gravitational waves, scientists are gradually piecing together the enigmatic nature of neutron stars. These celestial objects, despite their extreme properties, offer valuable clues about the fundamental laws that govern the universe. Each discovery, no matter how small, brings us closer to unraveling the mysteries of these fascinating objects. One of the most fascinating aspects of neutron stars is the phenomenon of starquakes. These events occur when the surface of a neutron star experiences immense stresses due to its extreme density and rapid rotation. The intense gravitational pull and the star's rotation create forces that build up over time. When these forces exceed the strength of the star's crust, it cracks, releasing vast amounts of energy in the form of radiation, much like an earthquake on Earth. This release can create ripples in space and generate bursts of gamma radiation. These star quakes can also affect the star's rotation speed, leading to phenomena known as glitches, where the star suddenly speeds up. Studying these events provides valuable insight into the bizarre physics that govern these objects and the behavior of matter under extreme conditions. Inside neutron stars, the conditions are so extreme that ordinary matter behaves in ways that are entirely unlike anything we observe on Earth. At the core of these stars, the pressure and temperature are so high that atomic structures break down. In these extreme environments, neutrons, normally found inside atomic nuclei, become the dominant particles. This state of matter is known as neutron degenerate matter. However, there is also the possibility of even more exotic forms of matter existing within neutron stars. One such state is the quark-gluon plasma, a phase of matter that scientists believe existed just after the Big Bang. In this state, quarks and gluons, the fundamental particles that make up protons and neutrons, roam freely without forming stable particles. Additionally, neutron stars might contain hyperons, particles that include strange quarks, which are heavier than the more common up and down quarks. These hyperons could contribute to the star's mass and play a role in its overall stability. Another theoretical possibility is the presence of magnetic monopoles. These hypothetical particles would carry only one type of magnetic charge, unlike ordinary magnets that have both a north and south pole. If they exist, magnetic monopoles could play a significant role in the complex magnetic environment of neutron stars. The study of these exotic forms of matter pushes the boundaries of our understanding of the fundamental forces that shape the universe. Neutron stars are not only important for what they reveal about the cosmos, but they also offer a unique laboratory for testing the most extreme physical conditions known to science. Each discovery about these stars helps scientists refine their models of matter, energy, and the laws of physics themselves. Neutron stars are also among the hottest objects in the universe. When a massive star collapses, the resulting neutron star generates immense heat. The surface temperature of a neutron star can exceed several 100,000 degrees, making it far hotter than the surface of the Sun, which is only around 6,000 degrees Celsius. Some neutron stars can begin their lives with temperatures exceeding 1,000,000 degrees, and even as they age, their surface temperatures remain much higher than those of most planets or other stellar remnants. For comparison, Earth's surface temperature ranges from cold to moderately warm, a tiny fraction of the extreme heat found on neutron stars. These high temperatures are a result of the tremendous gravitational forces that compress the core of the star, generating vast amounts of heat. As the neutron star ages, it may cool down, but even after billions of years, its surface temperature remains far higher than most objects in the universe. This combination of extreme heat, intense gravity, and the bizarre nature of the material inside makes neutron stars some of the most fascinating and difficult objects to study in all of astrophysics. In the end, the study of neutron stars reveals not only the extraordinary nature of these objects, but also the fundamental mysteries of the universe itself. By continuing to develop new technologies and techniques, scientists hope to uncover more secrets about these elusive stars, further expanding our understanding of the cosmos and the laws of physics that govern it. Neutron stars, born from the explosive death of massive stars, are among the most captivating and extreme objects in the universe. When a star exhausts its nuclear fuel, it undergoes a supernova explosion, a cataclysmic event that compresses its core under the immense force of gravity. As the core collapses, protons and electrons combine to form neutrons, creating a compact, incredibly dense remnant. This neutron star, although no larger than a city, can contain more mass than our Sun. This immense density results in extreme gravitational and magnetic fields, giving rise to a multitude of fascinating phenomena. One of the most striking characteristics of neutron stars is their emission of radiation, which can vary greatly in type depending on the environment surrounding them. As a neutron star spins, it can emit beams of radiation from its magnetic poles. These beams often consist of radio waves, X-rays, and gamma rays, and their detection can reveal much about the star's behavior and properties. A specific type of neutron star, known as a pulsar, rotates at an incredibly fast pace. As it spins, charged particles become trapped in its magnetic field, and these particles are accelerated to such high speeds that they emit bursts of radio waves. These waves are emitted in pulses, much like the beam of a lighthouse, and we only detect them when the beam sweeps across our line of sight. The process that leads to the emission of X-rays and gamma rays from neutron stars is equally fascinating. These high-energy forms of radiation are typically produced when matter from a companion star interacts with the neutron star's intense gravitational field. As the companion star loses material, this material spirals inward, heating up dramatically as it is accelerated toward the neutron star's surface. This heat causes the matter to emit X-rays as it nears the star. In other cases, when particles are caught in the neutron star's magnetic fields, they gain enough energy to produce gamma rays, further highlighting the extraordinary conditions present in these objects. Neutron stars thus function as cosmic laboratories, where fundamental physics operates under extreme conditions. The various types of radiation they emit, radio waves, X-rays, and gamma rays, offer astronomers a unique opportunity to study these fascinating objects and learn more about the universe's most extreme environments. The radiation reveals critical information about the star itself, while also providing insights into the fundamental laws that govern the cosmos. However, the impact of neutron stars extends far beyond their own emission of radiation. The intense gravitational and magnetic forces exerted by these stars influence their surrounding environments in profound ways. For example, neutron stars can strip atmospheres from nearby planets, strip away organic material, and even alter the surface of these planets. The closer a planet is to the neutron star, the more devastating these effects can be. For a planet positioned close to a neutron star, the radiation might be strong enough to ionize its atmosphere, essentially turning the planet into a barren wasteland. Even if a planet is farther away, it may still experience significant radiation exposure, leading to atmospheric stripping and other forms of environmental damage. Additionally, neutron stars can interact with the interstellar medium, the gas and dust that fills the vast spaces between stars. Their powerful magnetic fields and radiation can compress surrounding gas clouds, triggering the formation of new stars. In this way, neutron stars not only influence the environments of nearby planets, but also play a pivotal role in the broader processes that govern star formation. Through these interactions, neutron stars contribute to the cycle of matter in the universe, both as the remnants of dying stars and as catalysts for new star birth. The influence of neutron stars on their surroundings is not limited to radiation and magnetic effects. Their immense mass and gravitational pull can also have significant consequences for the dynamics of nearby celestial bodies. If a neutron star is part of a binary system, where it is paired with another star, it can pull material from its companion. This interaction creates an accretion disk, a swirling disk of gas and material being drawn toward the neutron star. As the material spirals inward, it heats up and emits X-rays, providing yet another way for astronomers to observe these objects. The gravitational interaction between a neutron star and its companion star can also affect the life cycle of the second star. If the neutron star draws too much material from its companion, the companion star may exhaust its nuclear fuel more quickly than expected, causing it to evolve into a red giant earlier than it would have otherwise. This kind of interaction showcases the powerful gravitational influence that neutron stars exert, not only altering the orbit and structure of nearby stars, but also accelerating their evolution. In addition to its effects on nearby stars, the gravitational field of a neutron star has a profound impact on space itself, bending and distorting the very fabric of space-time. Space-time can be envisioned as a flexible sheet, and when a heavy object like a neutron star is placed on this sheet, it causes a deep depression. This bending of space-time is what creates gravity, and the closer one is to the neutron star, the stronger the gravitational pull they will experience. Light traveling near the neutron star is affected too, bending as it passes through the distorted spacetime. This phenomenon, known as gravitational lensing, causes stars in the background to appear stretched or multiplied around the neutron star. Time itself is also influenced by the intense gravity of neutron stars. In stronger gravitational fields, time runs slower. Thus, an observer far from the neutron star would witness events occurring close to it in slow motion, further illustrating the profound relationship between mass, gravity, and the fabric of space-time. These effects, gravitational lensing, the warping of space-time, and the slowing of time, are all manifestations of the extraordinary way neutron stars influence their surroundings. Neutron stars, in essence, are cosmic powerhouses that serve as both the remnants of once massive stars and the drivers of a host of dynamic processes in their environments. Through their extreme density, powerful radiation, and intense gravitational fields, they shape the very nature of space around them. They interact with nearby stars, affect the interstellar medium, and contribute to the ongoing cycle of star birth and death. Their existence challenges our understanding of the universe and offers invaluable insights into the fundamental forces that govern it. Through studying neutron stars, astronomers are not only uncovering the secrets of these dense cosmic objects, but also learning more about the underlying principles of physics. The unique conditions surrounding neutron stars allow researchers to test theories of general relativity, explore the behavior of matter under extreme pressure, and better understand the fundamental forces of nature. The radiation they emit, the effects they have on their surroundings, and the profound influence they exert on space-time all provide a rich source of data that continues to inform our understanding of the universe at its most extreme. In a way, neutron stars stand as both the ultimate endpoint for massive stars and the beginning of new cosmic processes. As they form from the remnants of dying stars, they launch new cycles of star formation and influence the evolution of the universe. Their radiation, magnetic fields, and gravitational forces remind us of the incredible complexity and interconnectedness of the cosmos, where even the most extreme objects contribute to the ongoing story of the universe's development. The powerful gravitational field of a neutron star is far-reaching, capable of influencing the paths of objects within a vast region. Planets, moons, and even distant stars in the vicinity can have their orbits altered, sometimes in dramatic ways. These distortions can lead to collisions between celestial bodies, or, in some cases, send them spiraling into new and unexpected trajectories. Such events can have profound consequences, particularly when it comes to the stability of planetary climates, or the potential for life. In extreme cases, a neutron star, if it forms close enough to a massive star system, can strip away enormous amounts of material, so much so that the very structure of the surrounding matter is altered. Over time, this could result in the formation of new stars from the remaining gas and debris. This incredible gravitational influence creates ripple effects across the galaxy, shaping the orbits and fates of countless celestial objects over millions of years. In a sense, neutron stars are both architects and destroyers of the cosmos, their actions influencing the evolution of entire star systems and interstellar structures. They serve as dynamic forces, constantly interacting with the universe around them, leaving an indelible mark on their surroundings. Neutron stars are among the densest objects in the universe, formed from the remnants of supernova explosions. These stellar remnants are so compact that a single cubic centimeter of neutron star material weighs about 4 billion tons, an incomprehensible density when compared to ordinary matter. As researchers continue to probe the mysteries of these fascinating celestial objects, they are making exciting strides in various areas of astrophysical research. One major area of investigation is understanding the behavior of matter under the extreme conditions found within neutron stars. The matter inside these stars is packed so tightly that the typical structure of atoms and molecules is broken down. Physicists are eager to learn how individual particles, atoms, and even entire nuclei behave in such an environment, as it could shed light on the fundamental nature of the strong nuclear force that binds protons and neutrons together. This research could lead to revolutionary insights into the very building blocks of matter. Another critical area of study involves gravitational waves, ripples in the fabric of space-time caused by massive objects accelerating through space. When two neutron stars collide, they release an enormous amount of energy, sending out these gravitational waves that spread across the universe. The detection of these waves has opened up a new frontier in astrophysics, offering scientists a real-time view of these extraordinary cosmic events. As observatories and detection technology improve, scientists are gaining an increasingly detailed picture of neutron star mergers and their aftermath. These events are thought to be responsible for the creation of heavy elements like gold and platinum, making neutron star collisions crucial to understanding the processes that forge the universe's most valuable materials. Neutron stars also serve as cosmic laboratories for testing theories of fundamental physics. The extreme gravitational and electromagnetic fields surrounding these stars present a unique opportunity to challenge and refine our current understanding of the laws of physics. For instance, one of the most fascinating questions is how light behaves near a neutron star, where gravity is so intense that it warps space-time itself. This could provide insights that challenge existing models of general relativity and help scientists refine their understanding of how the universe operates on the most fundamental level. The advent of new observational technologies is revolutionizing the study of neutron stars. Upcoming space telescopes are expected to capture higher resolution images and more data than ever before, offering unprecedented insights into the properties of these incredible objects. These advancements will allow scientists to study neutron stars' magnetic fields, rotation rates, and surface characteristics in incredible detail. Observing these features will be key to understanding how neutron stars function and evolve over time. Modern space telescopes are designed to detect a wide range of light, from visible wavelengths to more energetic forms like X-rays and gamma rays. Neutron stars, however, are often hidden from view in ordinary light due to their extreme gravity and dense material. Their intense magnetic fields and rapid rotations make them prime sources of X-rays and other radiation, particularly if they are part of a binary system, drawing material from a companion star. New telescopes that can specifically capture these types of emissions will provide clearer, more detailed images of neutron stars, unveiling their hidden features and allowing for a more complete understanding of their behavior. Moreover, recent advancements in observational technology have significantly improved the sensitivity and resolution of telescopes. This means that even the faintest signals emitted by distant neutron stars can now be detected, revealing details that were once too subtle to observe. This enhanced capability allows scientists to measure properties like the star's magnetic fields, their rotation speeds, and the nature of their interiors. All of these factors are crucial for building a comprehensive model of neutron star physics and understanding how they fit into the broader context of stellar evolution. With the development of adaptive optics and improved data processing techniques, telescopes are becoming better at reducing distortions caused by the Earth's atmosphere and other sources of noise. This increased clarity makes it possible to observe neutron stars with greater precision, even from Earth's surface. It also allows astronomers to study a larger number of neutron stars simultaneously, helping to identify patterns and behaviors across different objects. The ability to observe neutron stars more clearly and in greater detail is crucial for identifying new discoveries and gaining insights into the cosmic processes that govern their existence. The ability to capture more specific and detailed information about neutron stars' emissions is a game changer for the field of astrophysics. As new technologies continue to evolve, scientists will be able to unlock deeper insights into the universe's most extreme environments. These observations will not only enhance our understanding of neutron stars themselves, but will also provide valuable information about the fundamental laws of physics that govern the universe. Whether through the study of gravitational waves, the behavior of matter under extreme conditions, or the properties of neutron stars' magnetic fields and rotations, each new discovery brings us closer to understanding the vast and mysterious universe we inhabit. Additionally, advanced data analysis techniques are revolutionizing our ability to study neutron stars. These sophisticated methods allow astronomers to sift through massive amounts of information, extracting valuable insights from the complex patterns of light and radiation emitted by these objects. Neutron stars rotate at incredibly high speeds, emitting beams of electromagnetic radiation akin to lighthouse beams. By observing these emissions, scientists can learn about a star's magnetic fields, internal structure, and rotational behavior. With improved data processing, even the faintest signals from neutron stars can now be detected and analyzed, revealing hidden details about their composition, behavior, and evolution. This enhanced ability to analyze data is critical because it allows scientists to gain a better understanding of various aspects of neutron star physics, such as surface temperature, which can provide valuable clues about their age and evolutionary history. By studying these properties, researchers can track the life cycle of neutron stars and learn more about their role in the cosmic ecosystem. In conclusion, neutron stars are not only among the densest and most extreme objects in the universe, but they also serve as essential tools for advancing our knowledge of fundamental physics. Through advancements in observational technology and data analysis techniques, scientists are unlocking the secrets of these enigmatic objects. Whether studying the behavior of matter under extreme conditions or the formation of heavy elements, neutron stars continue to reveal their mysteries, offering new insights into the very fabric of the universe. Improved analysis plays a crucial role in expanding our understanding of some of the most mysterious and extreme phenomena in the universe. A prime example of this is the study of neutron star collisions. These cosmic events, when two neutron stars spiral toward each other and eventually collide, have the ability to generate gravitational waves, which are ripples in the very fabric of space-time. But that's not all. These catastrophic events can also forge heavy elements, including gold, an incredibly significant discovery for both astrophysics and chemistry. The formation of these elements in such extreme environments could forever change how we view cosmic history, the origins of elements and spherulites, and the process through which heavier atoms come into existence. As we continue to analyze the data collected from a variety of detectors and telescopes with increasing precision, we can begin to form much richer, more detailed models of the life cycle of neutron stars, as well as the fundamental physics at play within these dense and enigmatic objects. The closer we get to understanding neutron stars, the more we push the boundaries of current theoretical frameworks. These objects, which are the remnants of massive stars that exploded in supernovae, represent one of the most extreme states of matter that exists in the universe. Their study challenges our understanding of physics, particularly when it comes to the behavior of matter under such dense and extreme conditions. And as the analysis improves, it offers a unique opportunity to test the limits of our theories about how matter behaves in the most intense environments. This process of discovery not only deepens our understanding of the universe, but could also reveal entirely new realms of physics that we never before thought possible. In this endeavor, international collaboration is absolutely essential. Neutron stars, due to their complexity and the extreme environments in which they exist, cannot be fully understood by any one group or nation working alone. By joining forces across the globe, scientists can share their expertise, resources, and technologies, creating a much more robust framework for advancing research. The study of neutron stars is inherently interdisciplinary, requiring input from a wide range of scientific fields, including physics, astronomy, and computational modeling. When researchers from different countries pool their resources, they gain access to some of the most powerful and cutting-edge telescopes and observatories on Earth, many of which are strategically placed around the world to observe different aspects of astronomical events. These observatories are capable of capturing the full spectrum of radiation emitted by neutron stars, from visible light and radio waves to X-rays and gamma rays, each wavelength offering unique insights into the nature of these stellar remnants. By combining these observations from around the world, scientists can develop a far more comprehensive and nuanced understanding of neutron stars and their behavior. They can begin to decipher the way in which gravitational waves, for example, manifest during the collision of neutron stars. These gravitational waves provide a direct signal of the event itself and can be detected from vast distances, allowing scientists to study neutron star collisions even when the stars involved are located billions of light years away. But collaboration goes beyond just data sharing. It also provides a platform for global discussions that accelerate scientific progress. Specialized workshops, conferences, and symposiums bring together the brightest minds in the field, allowing them to exchange ideas, share findings, and brainstorm new approaches. These forums of intellectual exchange lead to innovative new theories and experimental techniques, continually pushing the envelope of what is possible in neutron star research. Additionally, when teams from diverse cultural backgrounds come together, creativity thrives. Different perspectives allow for new ways of thinking, which can lead to breakthroughs in solving long-standing mysteries about neutron stars and the fundamental forces of nature. With the advent of sophisticated technologies like supercomputers and highly advanced simulation software, international cooperation has opened up entirely new possibilities for modeling the behavior of neutron stars. These computational models allow scientists to recreate the extreme environments found in these dense objects with incredible accuracy, making it possible to simulate conditions that are impossible to replicate on Earth. By pooling their collective expertise and resources, international teams are now able to create simulations that can accurately predict the behavior of matter in neutron stars, including the incredibly dense and unusual states of matter that exist within their cores. This kind of international synergy is transforming the study of neutron stars from a series of isolated research projects into a global scientific undertaking. With the combined intellectual resources, computational power, and observational tools of numerous countries, we are now better equipped to tackle the many mysteries that surround these objects. The result is a truly collaborative effort that promises to accelerate discoveries and push the boundaries of astrophysics in ways that were once thought to be out of reach. In addition to the collaborations happening on Earth, there is an increasing interest in spacecraft missions that could significantly enhance our understanding of neutron stars. These missions, particularly those designed to explore neutron stars directly, could bring a wealth of new data and insights. Neutron stars are the remnants of stars that have undergone supernova explosions, and their cores are compressed to such extraordinary densities that they offer a natural laboratory for studying extreme physics in ways that cannot be replicated in any terrestrial laboratory. One of the most promising contributions a spacecraft could make is through its ability to capture electromagnetic radiation emitted by neutron stars. With advanced telescopes on board, these spacecraft could observe neutron stars in a wide range of wavelengths: visible light, X-rays, and even gamma rays. Each of these wavelengths provides distinct information about the star's temperature, magnetic field, composition, and even the processes occurring within its interior. By carefully analyzing this radiation, scientists can begin to unravel the complex life cycle of neutron stars, their magnetic fields, and the physical processes that govern their behavior. Moreover, spacecraft missions could directly measure the gravitational waves produced by neutron stars, particularly those that exist in binary systems. When two neutron stars in such a system collide, they produce ripples in the fabric of spacetime that travel across the universe. These gravitational waves can be detected by specialized instruments, allowing scientists to study these cataclysmic events in unprecedented detail. The ability to measure gravitational waves directly would not only provide new insights into neutron stars, but also deepen our understanding of gravity, one of the four fundamental forces that govern the universe. Beyond the study of radiation and gravitational waves, spacecraft missions could provide invaluable data about the behavior of matter in the extreme environments found within neutron stars. The gravitational forces in these objects are so intense that they create conditions where normal physics breaks down, offering an unparalleled opportunity to explore theories of quantum mechanics, nuclear interactions, and other fundamental aspects of physics. Understanding how matter behaves in such extreme conditions could lead to new breakthroughs in our understanding of the universe and could help us to refine or even revise current theories of physics. In the end, Whether through the data collected from global collaborations or through direct observations from spacecraft missions, the study of neutron stars is advancing at a rapid pace. Together, scientists are embarking on an exciting journey of discovery that promises to transform our understanding of the universe and the fundamental laws of nature. A mission that targets neutron stars could revolutionize our understanding of these enigmatic objects and unveil the secrets of their magnetic field, some of the most powerful in the known universe. These magnetic fields shape the behavior of neutron stars in profound ways, influencing everything from the star's radiation emissions to its rotation and overall stability. By studying the complexities of these magnetic forces, we would gain deeper insights into the life cycles of massive stars, shedding light on the mysteries of stellar evolution. Future spacecraft missions dedicated to neutron star exploration offer the possibility of unlocking these secrets, vastly expanding our comprehension of the universe's most extreme environments and enriching our understanding of the fundamental laws that govern nature itself. Yet the potential dangers that arise when a celestial body like a neutron star comes too close to Earth are extraordinary and catastrophic. Neutron stars are remnants of supernova explosions condensed into incredibly dense objects. Their mass is concentrated into a sphere no larger than a city, but even this small size houses an immense density. This extreme compactness results in an overwhelming gravitational pull, one so strong that it can warp the fabric of space-time itself. If Earth were to be drawn closer to such an object, the effects would be devastating. The first noticeable consequence would be an intense and sudden increase in gravity. The gravitational pull of the neutron star would generate immense tidal forces, far more powerful than those caused by the moon. Oceans would surge, flooding coastal regions, while solid ground would experience tremendous strain. Entire tectonic plates could buckle under the pressure, and certain areas of the Earth might crack or even break apart entirely. As Earth draws nearer, these effects would intensify. The gravitational forces would distort the planet in unimaginable ways, stretching it like dough under a rolling pin. This process, known as spaghettification, occurs when the difference in gravitational pull between two sides of an object becomes so great that it is torn apart. As the Earth approaches the neutron star, its surface could be stretched and shredded, with the planet torn to pieces in a matter of time. In addition to the gravitational forces, the radiation emitted by the neutron star would be another deadly threat. These stars are known for emitting intense beams of radiation, including high-energy particles and powerful light waves. As this radiation bombards Earth, it could strip away the atmosphere, leaving the planet completely exposed to the vacuum of space. Without an atmosphere to shield it, Earth's surface would become inhospitable. Temperatures would plummet and the environment would become unrecognizable, hostile to all forms of life. The once protective blanket of gases that shield our planet from the harsh realities of space would vanish, leaving Earth vulnerable to the full force of the cosmos. In the worst-case scenario, if Earth were to venture too close, it would likely be obliterated, its components absorbed by the neutron star and scattered into the void of space. The planet's remains would be forever lost, dissolved into the stellar heart of a neutron star. This catastrophic scenario provides a glimpse into the overwhelming power and forces of nature. It reminds us how fragile our existence truly is within the vastness of the universe, where life as we know it is balanced precariously on the edge of chaos. The prospect of a neutron star entering our solar system would be a defining moment in the history of our planet. Neutron stars, in their incredibly dense and powerful nature, are remnants of supernova, the explosive deaths of massive stars, and their presence would create irreversible changes within our solar system. The first and most immediately noticeable effect would be the immense gravitational pull exerted by the neutron star as it approached. As the object neared, its gravity would wreak havoc on the delicate orbits of nearby celestial bodies, including planets, comets, and asteroids. The trajectories of these objects would become unstable, causing them to collide, orbit unpredictably, or be flung into the outer reaches of the solar system. Planets, once in stable orbits, might be pulled into the neutron star's grasp, while others could be cast out into the cold expanse of interstellar space. This dramatic shift would initiate a chaotic reorganization of the solar system, replacing the tranquil and predictable movements of the planets with violent disruption and upheaval. While the gravitational effects would be catastrophic, the radiation emitted by the neutron star would pose an equally serious threat. Neutron stars are notorious for their emission of X-rays and other forms of high-energy radiation. If one were to venture close enough to Earth, this radiation would have devastating effects on our planet. It could strip away the atmosphere, exposing the surface to the unforgiving environment of space. Without the protection of our atmospheric shield, the surface of Earth would become vulnerable to solar winds and cosmic rays, and the once hospitable environment would transform into a barren wasteland. The presence of a neutron star within the solar system would not just be a gravitational threat, but an existential one, radically altering the balance of life and potentially rendering Earth uninhabitable. Moreover, the arrival of such an exotic stellar object would trigger tidal forces capable of instigating destructive geological activity on Earth. These tidal forces, amplified by the immense gravity of the neutron star, could cause widespread earthquakes, volcanic eruptions, and other geological disturbances. The planet's surface would experience tremendous strain, and previously stable regions could become centers of catastrophic change. The influence of the neutron star would likely bring about irreversible shifts in the solar system structure, replacing the orderly procession of orbits and seasons with a chaotic dance of celestial bodies. Earth, along with the other planets, would be caught in the unpredictable currents of this cosmic upheaval. In a situation where a neutron star entered our solar system, the familiar rhythms of life and cosmic order would be replaced by chaos and uncertainty. The predictable orbits of the planets, the steady cycles of day and night, and the regularity of the seasons would all be thrown into disarray. The presence of this singularly powerful object would redefine the very nature of existence in our solar neighborhood. Earth's once stable environment would no longer be a sanctuary but a battleground, a place where the forces of gravity, radiation, and celestial violence continually reshape the landscape. Living on a planet in such a turbulent environment would pose extreme and almost insurmountable challenges. Neutron stars, born from the catastrophic death of a massive star, are some of the most extreme objects in the universe. Their density is so profound that even a small fragment of a neutron star's material would weigh far more than the largest mountains on Earth. The gravity on a planet near such a star would be intense, so strong that nothing would be able to escape its pull. This immense gravity would distort the environment in ways that would make survival difficult, if not impossible. The greatest danger to life, however, comes from the intense radiation that neutron stars emit. These stars often generate powerful beams of radiation, including X-rays and gamma rays, which are lethal to living organisms. If Earth found itself within the reach of such radiation, survival would be almost impossible without the kind of advanced shielding we can only dream of. The surface of the planet would experience extreme temperature fluctuations, depending on its proximity to the star and the intensity of the radiation. In some areas, the temperatures could plunge to sub-zero levels, while in others, they could rise to levels that would incinerate any exposed material. Weather patterns, if they existed at all, would be chaotic, with storms of unparalleled intensity. A planet in the vicinity of a neutron star would become an inhospitable wasteland, with the forces of nature pushing all life toward extinction. The survival of humanity and other life forms would depend entirely on the development of technologies capable of shielding against the radiation and gravity, and even then, such survival would be a temporary reprieve at best. The extreme and unpredictable conditions of life near a neutron star would be a stark reminder of the delicate and fragile nature of existence in the cosmos. A planet in close proximity to a neutron star would find itself under an intense array of forces that would make it nearly impossible for life to survive. The gravitational pull of the neutron star would create powerful tidal forces, potentially destabilizing the planet's geological structure. These forces could induce frequent earthquakes, volcanic eruptions, or other tectonic activity, shaking the planet's surface relentlessly. The sheer gravitational influence might stretch the planet's crust, leading to fractures and lava flows, making the environment tumultuous and hazardous. At the same time, any atmosphere that might exist on the planet would likely be thin, if not completely absent. The combination of proximity to such a dense and powerful object and the constant battering from radiation would make it difficult for essential elements like air and water to coexist. The conditions would be hostile to the formation of complex ecosystems, as basic building blocks for life would be absent or constantly under threat. The question arises, could life as we know it exist under such extreme conditions? The answer seems all but impossible, given the overwhelming forces at play. The presence of a neutron star near a planet presents multiple existential challenges: radiation, gravitational extremes, temperature fluctuations, and geological disruptions, each of which would act in tandem, creating a nearly uninhabitable environment. Even if life were to find a foothold in such an environment, it would have to contend with an incessant barrage of destructive forces. Moreover, the very nature of neutron stars presents a unique and formidable set of challenges. Neutron stars are the remnants of massive stars that have exploded in supernova events. These stars, once capable of shining brightly across the universe, collapse in on themselves, creating a super-dense core that packs more mass than our sun into a space no larger than a city. The resulting gravitational and magnetic fields are extraordinarily powerful, and their reach extends far beyond the remnants of the star itself. If a neutron star were to venture too close to our solar system, the consequences could be catastrophic. The most immediate and significant impact would stem from its immense gravitational pull. The gravitational field of such an object is so intense that it could disturb the orbits of nearby planets, moons, asteroids, and other celestial bodies. Even a minor shift in the gravitational forces acting on Earth could lead to dramatic changes in our orbit around the Sun. This slight alteration in distance from the Sun could trigger profound changes in the seasons, disrupting ecosystems that have evolved over millions of years. The amount of solar energy Earth receives might fluctuate, causing widespread climate shifts and even affecting the fundamental balance of life on the planet. Beyond the gravitational effects, neutron stars emit tremendous bursts of radiation. These bursts, including intense beams of X-rays and gamma rays, are some of the most powerful forms of energy in the universe. If a neutron star were positioned close enough to Earth, these rays could reach our planet, stripping away parts of our atmosphere. This would expose life on Earth to a level of radiation that could be catastrophic, significantly altering the conditions for survival. The atmosphere, which protects us from harmful cosmic radiation, would be compromised, and as it thinned, more radiation would penetrate the surface. This could result in an increase in the harmful effects of solar radiation, putting plants, animals, and even the very foundation of our food chains at risk. Not only would the radiation threaten life, but the presence of a neutron star could also interfere with the dynamics of space weather. Neutron stars are surrounded by powerful electromagnetic fields which could interact with the solar wind, charged particles released by the sun. This interaction could amplify solar phenomena, leading to more intense auroras and more frequent solar storms. Satellites and communication systems on Earth would be at greater risk, potentially causing widespread disruptions in technology and communications. In addition to the radiation and gravitational pull, the electromagnetic fields of a neutron star could fundamentally alter how Earth's atmosphere interacts with the solar wind. If a neutron star were too close, its magnetic field might distort the behavior of charged particles in the solar wind, resulting in more severe space weather. This could alter our climate, disrupt electrical grids, and affect the overall stability of Earth's atmosphere, making it even harder for life to thrive. As a consequence, the presence of a neutron star within our solar system would create a series of cascading effects, each exacerbating the other, and ultimately leading to an environment where life as we know it would find it extremely difficult, if not impossible, to survive. The delicate balance of forces that currently allows life to flourish on Earth would be profoundly disrupted by the gravitational pull, radiation, and electromagnetic influences of a nearby neutron star. Neutron stars, by their very nature, are some of the densest objects known to humanity. These stars, formed from the remnants of massive stars that have exploded in supernova events, condense into a core so dense that a single cubic centimeter of neutron star material would weigh as much as a mountain. The forces within these objects are so extreme that they are beyond any earthly comparison. The gravitational field surrounding them is so intense that it warps the very fabric of space and time itself. The proximity of a neutron star would have profound effects not only on the environment of a nearby planet, but also on the larger structure of the solar system. Imagine the balance of a scale, where the sun holds the planets in their orbits with a delicate gravitational pull. Now, introduce the mass of a neutron star into this balance, and the scale tips. The gravitational tug of a nearby neutron star could distort the orbits of planets, moons, asteroids, and comets. This could lead to chaotic shifts in planetary positions, potentially ejecting some planets from their orbits or causing them to collide with other celestial bodies. The already fragile stability of the solar system would become even more unpredictable, raising questions about the long-term viability of planetary orbits. The disruption of the gravitational balance would extend to the interaction between the sun and its planets. A neutron star's influence on the solar system would change the dynamics of planetary movement, potentially altering how planets interact with one another. In such a scenario, the stable orbits that we have come to rely on would become unstable, leading to unpredictable trajectories and creating a more chaotic and turbulent solar environment. Ultimately, a neutron star is not just a distant astronomical phenomenon. Its presence in a solar system would create a seismic shift in the fabric of that system, causing significant changes that could disrupt the delicate balance of forces that has allowed life to thrive. From the radiation it emits to the gravitational pull it exerts, the very existence of a neutron star near a planet would raise profound challenges. If such a star were to come too close, the planet would face an environment so extreme that the possibility of sustaining life would seem nearly impossible. The conditions near a neutron star are a stark reminder of how fragile the existence of life is, and how easily the delicate equilibrium that sustains it can be disrupted. Scientists are constantly exploring the question of what defines life on Earth, but recent discoveries have forced us to broaden our understanding of life's potential. Throughout history, organisms have been discovered thriving in some of the most extreme and unexpected environments, places once thought to be too hostile to support life. From the darkest depths of the ocean, around deep-sea vents where no light penetrates, to the scorching acidity of highly acidic lakes, and even the frozen, barren tundras where temperatures plummet far below freezing, life has been found in places where few could imagine it surviving. In fact, some of the organisms that exist in these extreme environments, known as extremophiles, have shown us that life can be far more resilient and adaptable than previously thought. These extraordinary creatures demonstrate how life in its many forms is capable of surviving in conditions that defy what we once believed were the limits of habitability. If we were to consider life near a neutron star, one of the most extreme environments in the universe, it would likely be vastly different from what we know. Life near such a star would have to rely on radically different biochemical processes, perhaps based on non-carbon chemistry, to survive. It might utilize unknown biochemical pathways that allow it to withstand the intense radiation, unimaginable pressure, and temperature extremes found in such a place. These theoretical forms of life would likely need to exist in a delicate balance, navigating the most dangerous regions of the star's surroundings, exploiting any available resources while avoiding the most perilous areas. The chances of familiar life as we know it thriving near a neutron star remain incredibly low, but the very notion of it sparks curiosity. It forces us to confront a profound truth about the universe. It is filled with mysteries that continually challenge our understanding of biology. As scientists delve deeper into the limits of life, they acknowledge that the universe is home to an almost unimaginable variety of environments, many of which could harbor life forms entirely different from anything we've ever known. If organic molecules, complex compounds made from carbon, were to be discovered near a neutron star, it would revolutionize our thinking. These molecules are the very building blocks of life, and their presence in such a harsh environment could suggest that life's essential ingredients are far more widespread across the cosmos than we had ever imagined. These molecules could form through a variety of chemical processes, some of which might defy our current understanding of how life begins. Despite the extreme conditions near a neutron star, the presence of organic molecules would suggest that life's fundamental building blocks could survive, or even form, in these environments. Such a discovery would radically challenge our concept of where life can exist, encouraging scientists to explore the most extreme corners of the universe in search of life. If life could begin near a neutron star, in an environment we once deemed inhospitable, it would open the door to the possibility of life elsewhere in the universe, on other planets and celestial bodies that face extreme conditions, far beyond what we considered survivable. Moreover, studying these molecules would offer new insights into the resilience of chemical compounds and the potential pathways to life, expanding our understanding of the adaptability of life forms. We might discover life not just in the forms we know, but in novel forms we cannot yet even imagine. This discovery could redefine our perceptions of what it means to be alive, offering an entirely new chapter in the story of life in the cosmos. Neutron stars themselves are among the most fascinating and enigmatic objects in the universe. They are the remnants of massive stars that have exploded in a cataclysmic supernova. The gravity around a neutron star is so immense that it alters the very fabric of space-time, influencing the behavior of matter and energy in ways that are almost impossible to comprehend. If we were to consider how the proximity of a neutron star might impact the habitability of nearby exoplanets, several key factors would come into play. The gravity of a neutron star is so intense that any planet orbiting too close to it could be at risk of its orbit destabilizing. This could lead to catastrophic fluctuations in temperature, extreme shifts in environmental conditions, and a general environment hostile to life as we know it. The gravitational forces might be so powerful that they could even tear the planet apart, especially if it crosses a critical threshold known as the Roche limit. Additionally, neutron stars emit vast of radiation, including harmful X-rays and gamma rays. If an exoplanet is situated too close to the star, this radiation could strip away the planet's atmosphere. Without an atmosphere to shield it, the planet's surface would be bombarded with lethal radiation, rendering it inhospitable to life. Yet if a planet were located at the right distance, a so-called Goldilocks zone, it could maintain a more stable orbit, avoiding gravitational instability and radiation bombardment. In such a case, the conditions might be just right for life to take root, albeit under highly unusual and extreme circumstances. Moreover, the formation of celestial bodies in the vicinity of a neutron star could be influenced by the heavy elements produced during the star's supernova explosion. These elements could enrich the surrounding space, potentially providing the necessary materials to form planets or even support life. While the extreme conditions around a neutron star would pose significant challenges to habitability, at the right distance and with the right orbital dynamics, certain exoplanets might develop conditions suitable for life. The study of these intricate and complex interactions is essential for astrophysicists as they work to pinpoint the locations in the universe where habitable worlds could exist, especially in environments that were once considered far too extreme. Neutron stars, though incredibly dense and violent, might offer unique opportunities for understanding the formation of life in the most challenging of circumstances. Imagine a neutron star as a city-sized sphere made almost entirely of tightly packed neutrons, an object so dense that a single teaspoon of its material would weigh as much as an entire mountain. The energy released by these stars is incredibly intense, primarily in the form of radiation. If extraterrestrial civilizations were able to harness the power of these stars, the possibilities are immense. One potential way they might do this would be by building advanced structures in orbit around the neutron star, designed to capture and convert its immense heat and radiation into usable energy. These structures might even tap into the intense magnetic fields surrounding the star, providing an almost limitless source of power. Such energy could potentially fuel propulsion systems capable of powering spacecraft for interstellar travel, allowing civilizations to explore vast regions of space without relying on conventional propulsion technologies. With enough energy, these spacecraft could significantly reduce travel times between distant stars, opening up new frontiers for exploration. The exploration of neutron stars and their surrounding environments not only challenges our understanding of where life might exist, but also pushes the boundaries of what we thought was possible in terms of energy utilization and technological advancement. The potential for new discoveries in these extreme environments is endless, reminding us that the universe is far stranger, more complex, and more mysterious than we can even begin to imagine. The environment surrounding a neutron star offers an array of possibilities that could push the boundaries of science and technology far beyond our current comprehension. This extreme setting, shaped by forces unimaginable on Earth, gives rise to a fascinating realm of physics, one in which exotic materials might be created, or even entirely new phenomena could emerge. These peculiarities might hold the key to innovations that revolutionize technologies, such as energy manipulation or advanced manufacturing techniques. If we allow ourselves to imagine, intelligent life forms, if they exist, might have evolved the capability to harness the intense energy radiating from neutron stars, mastering it in ways that ensure their survival in this hazardous environment. They could devise mechanisms to shield themselves from the overwhelming radiation, perhaps constructing protective energy barriers or utilizing advanced forms of energy conversion. These technologies would allow them to tap into the power of the neutron star itself, fueling their civilization while navigating the harshest conditions in space. The energy produced by a neutron star is far from ordinary. It holds the potential to be harnessed for a wide array of applications, from power generation that could sustain entire civilizations to the propulsion of advanced spacecraft capable of traversing vast interstellar distances. Furthermore, this energy could even be utilized in the creation of extraordinary materials with unique properties that could not be produced under the conditions of a typical planetary environment. The possibilities are nearly limitless, stretching the boundaries of what we know about both the universe and the potential for life to adapt to and exploit its extreme environments. This idea of civilizations striving to tap into the incomprehensible forces of nature mirrors the boundless curiosity and ingenuity that may arise from the exploration of these stellar phenomena. Neutron stars, among the most dense objects known in the cosmos, have long intrigued not only scientists, but also science fiction writers and filmmakers. In many works of fiction, neutron stars are often imagined as exotic celestial bodies teeming with potential for adventure, exploration, and even peril. Picture, if you will, a scene where a spaceship is navigating the immense gravitational forces of a neutron star, where time itself becomes distorted, moments stretching into what feels like eternity. Such depictions evoke a profound sense of danger and awe, pushing audiences to contemplate the mind-bending physics that govern these remnants of massive stars. Within various narratives, neutron stars are frequently portrayed as powerful sources of energy, with their colossal magnetic fields producing phenomena such as pulsars. These rapidly spinning neutron stars emit intense beams of radiation, sweeping across space like cosmic lighthouses. The dramatization of these elements is a powerful tool, heightening tension as characters race against time to escape the lethal radiation or unpredictable forces emanating from these cosmic giants. The visuals of intense light beams cutting through the vastness of space not only captivate the viewer's imagination, but also emphasize the awe-inspiring science underlying these celestial objects. Some stories take a more speculative turn, exploring the potential consequences of human interactions with neutron stars. In these plots, characters might encounter gravitational tidal forces so immense that they distort the very fabric of their spacecraft, warping both matter and space itself. These narrative explorations allow for profound philosophical musings on the fragility of existence within the cosmos, as well as the awe-inspiring, often terrifying forces at play in the universe. Whether depicted as the setting for thrilling space adventures or as the focal point for more existential questions, neutron stars serve as a unique and versatile canvas for science fiction creators. They challenge us to consider not only the limits of human experience, but also our place in a vast, unfathomable universe. As audiences delve into these captivating stories, they encounter tantalizing concepts deeply rooted in real scientific understanding, ideas that make the universe feel both profoundly strange and endlessly intriguing. However, popular media often presents neutron stars in sensationalized ways, leading to several misconceptions about their true nature. One of the most common misunderstandings is the idea that neutron stars are simply a denser version of regular stars. In reality, neutron stars form under extreme conditions. When a massive star exhausts its nuclear fuel and collapses under its own gravity, its core is compressed to an astonishing degree. In this process, protons and electrons combine to form neutrons, resulting in an object of extraordinary density, one that is far beyond anything we experience on Earth. Another frequent depiction of neutron stars involves their portrayal as gigantic cosmic magnets. While it is true that they possess magnetic fields many times stronger than Earth's, popular media often exaggerates this characteristic. These magnetic fields are indeed powerful enough to generate remarkable radiation, but they do not create the spectacular visual effects that are sometimes depicted in movies or television shows. Similarly, while films often portray neutron stars as constantly emitting explosive bursts of energy, this is far from the truth. Neutron stars do not explode. Rather, they emit steady beams of radiation when their magnetic poles align with Earth. This phenomenon, known as a pulsar, creates periodic pulses of light that can appear like a lighthouse beam sweeping across space. The idea of a neutron star as a constantly violent object, then, is more fiction than fact. Moreover, many fictional narratives imply that neutron stars are relatively easy to reach or interact with. This, too, is a misconception. In reality, the extreme gravity, density, and radiation levels of these objects make them hostile environments for any form of human exploration or survival. The idea of landing on or visiting a neutron star may seem thrilling, but in terms of scientific plausibility, it strays far from reality. Additionally, the vast distances separating us from neutron stars are often overlooked in popular media, with these distant objects portrayed as more accessible than they truly are. Recognizing and understanding these misconceptions helps us to appreciate the true nature of neutron stars as fascinating but enigmatic remnants of stellar evolution. Despite the sensationalized portrayals in popular media, the creative exploration of neutron stars in science fiction often sparks real-world scientific curiosity and inquiry. As remnants of once massive stars, neutron stars hold secrets about the fundamental workings of the universe. Their unique properties, such as their intense gravity, rapid rotation, and powerful magnetic fields, captivate the imaginations of authors and filmmakers alike. These extreme environments present challenges for storytellers, but also offer a backdrop for exploring deep scientific concepts. For example, the potential for neutron stars to emit powerful radiation or gravitational waves, the ripples in space-time caused by cataclysmic events, can inspire scientists to investigate these phenomena further. When fiction aligns with scientific possibility, it not only fuels our imagination, but also drives the search for new answers to the mysteries of the cosmos. In the end, whether portrayed as dangerous, mysterious, or awe-inspiring, neutron stars challenge our understanding of the universe. They are not just subjects of scientific study, but also symbols of the unknown, a reminder of the vastness of space and the complexity of the forces that govern it. As we continue to explore these celestial wonders, we are constantly reminded of how much there is still to discover about the cosmos and our place within it. The portrayal of neutron stars in popular media and fiction has transformed them from mere scientific anomalies to captivating objects of exploration and imagination. These objects, born from the violent deaths of massive stars, often serve as an intriguing backdrop in stories of adventure and discovery. In these fictional representations, complex concepts, such as the intense gravitational forces and the dense nature of neutron stars, are often simplified, allowing them to become accessible to a broad audience. This simplification not only makes the science more digestible, but also sparks an interest in fields like astronomy and astrophysics. As a result, these stories can inspire individuals who might otherwise never consider engaging with such subjects, thus fostering a greater public interest in the cosmos. Such heightened interest can, in turn, affect scientific endeavors. With more public curiosity comes the potential for increased funding directed at research into the enigmatic properties of neutron stars. This funding could fuel more extensive observational campaigns, paving the way for technological advancements that might otherwise be delayed or overlooked. In essence, the very sensationalism that fiction lends to neutron stars has a tangible impact on the development of real-world science. As audiences are drawn into the grandeur of these cosmic bodies, they are indirectly contributing to the progress of humanity's understanding of the universe. Moreover, the representation of neutron stars in fiction often highlights their significance in the cosmic tapestry. These objects, which are born from supernova explosions, play a critical role in the formation of heavy elements, and they are integral to understanding how the universe evolves. Their portrayal in literature and film can drive interdisciplinary research as scientists seek to answer questions that bridge the gap between imagination and empirical observation. What might initially seem like pure fantasy in the pages of a science fiction novel can in fact stimulate genuine scientific inquiry. Researchers may find themselves testing the limits of their current knowledge, driven by the imaginative possibilities proposed in these fictional worlds. Neutron stars, as remnants of stellar explosions, are undoubtedly among the most fascinating objects in the universe. They are incredibly dense, with a mass greater than that of our sun, yet they occupy a volume no larger than that of a city. The sheer scale of their density creates a stunning juxtaposition with the limitations of the human mind, which struggles to grasp such extremes. In the world of fiction, this immense density becomes a fertile ground for storytelling, where characters venture to these stellar giants, risking life and limb to uncover their secrets. Imagine, for instance, a narrative in which explorers travel to a neutron star in search of an element so rare and so bizarre that it defies the known laws of physics. The journey is fraught with dangers as the immense gravitational pull of the neutron star distorts space and time, creating a dramatic tension that propels the story forward. In these stories, the gravitational force of the neutron star is not just a scientific fact. It becomes an obstacle, a literal barrier to human exploration. Characters struggle to survive in an environment where the laws of physics are pushed to their limits, and survival itself becomes an act of defiance against the unyielding forces of nature. This powerful gravitational field could lead to suspenseful scenarios where objects are pulled in and distorted, and even the passage of time becomes malleable, bending in response to the star's intense gravitational influence. These dramatic twists could stretch our imagination, prompting us to rethink how we perceive reality itself. The imaginative possibilities don't end with the laws of physics. In fictional depictions, neutron stars are often portrayed as having environments so extreme that they could harbor life forms vastly different from anything we might encounter on Earth. Imagine life thriving in powerful magnetic fields or surviving intense radiation, beings that have evolved to adapt to these harsh conditions. Such depictions open up intriguing avenues for exploring alien cultures, technologies, and forms of communication. These life forms might possess abilities or characteristics that defy our understanding of biology, challenging our assumptions about what constitutes life in the universe. Adding to the drama of neutron stars is their role as pulsars, neutron stars that spin rapidly, emitting beams of radiation that sweep across the cosmos like cosmic lighthouses. These pulsars could inspire narratives in which characters race against time to decode the signals embedded within these beams. Perhaps these signals are not just random emissions, but rather a message from an ancient, advanced civilization attempting to reach out across the vast emptiness of space. The interplay between science and fiction in such stories is profound, as writers weave together the real-world phenomena of neutron stars with the endless possibilities of the human imagination. This fusion creates rich worlds that captivate audiences while simultaneously introducing them to the mysteries of the universe. Each neutron star, in its real-world manifestation, serves as a reminder of how little we truly know about the cosmos. These cosmic remnants challenge our understanding of time, space, and the fundamental forces of nature. Through the lens of both science and fiction, neutron stars push the boundaries of human knowledge, encouraging us to question the very fabric of reality. Their existence forces us to confront the unknown, compelling us to explore new frontiers in our quest to understand the universe and our place within it. The birth of a neutron star is a cataclysmic event. When a massive star explodes in a supernova, the core that remains collapses under its own gravity, compressing the matter into a sphere so dense that the laws of physics as we know them can no longer be fully applied. The density is unimaginable. A single cubic centimeter of neutron star matter would weigh billions of tons on Earth, far heavier than anything we encounter in our daily lives. This collapse results in an object where ordinary matter behaves in extraordinary ways, challenging scientists to rethink everything we understand about the fundamental forces that govern our universe. The incredible gravitational forces at play in a neutron star create an environment where quantum mechanics, the theory that describes the behavior of particles on the smallest scales, meets general relativity, the theory that governs the behavior of gravity on the largest scales. In such extreme conditions, these two fundamental theories often clash, leaving scientists grappling with the complexities of how they interact. The behavior of matter under such high pressures and densities remains one of the great unsolved mysteries of modern physics. To make sense of it, researchers are forced to explore theories that go beyond the current models, reaching into realms of physics that have yet to be fully understood. Neutron stars also generate magnetic fields that are billions of times stronger than Earth's. These fields not only challenge our understanding of magnetism, but also lead to fascinating phenomena such as pulsars. A pulsar is a rapidly rotating neutron star that emits beams of radiation which sweep across space in a precise and predictable manner. These beams offer a unique opportunity to study time and space, as their regularity provides insights into the fundamental nature of the universe itself. The study of neutron stars, then, is not just about understanding a single cosmic object, but about exploring the very fabric of reality and the forces that shape our universe. In this pursuit, neutron stars become cosmic laboratories, where conditions cannot be replicated on Earth. In these stellar environments, the extremes of nature are laid bare, providing an unparalleled opportunity to test the limits of our knowledge. Each discovery about neutron stars brings us closer to understanding not only these remarkable objects, but also the larger questions about the universe itself. The study of neutron stars challenges our preconceived notions and inspires us to explore new dimensions of thought, constantly pushing the boundaries of human understanding. Ultimately, the study of neutron stars provides profound insights into the most fundamental aspects of physics. These objects are not only fascinating in their own right, but also serve as a gateway to understanding the forces that govern the cosmos. The more we learn about neutron stars, the closer we come to understanding the mysteries of the universe and our place within it. Each discovery adds another piece to the puzzle, revealing the deeper truths that lie hidden within the fabric of reality. Neutron stars are some of the most mind-boggling objects in the universe. They represent the final stages of the life cycle of massive stars, and their existence challenges and reshapes the way we think about physics, matter, and the cosmos itself. When a large star runs out of fuel, it undergoes a supernova explosion, violently shedding its outer layers. But the core, if massive enough, collapses under its own gravity, compressing the matter within into a compact, incredibly dense object, the neutron star. This transformation, where protons and electrons combine to form neutrons, results in an object that is almost entirely made up of these subatomic particles. A single cubic centimeter of neutron star material would weigh around 400 million tons, something utterly unimaginable to us on Earth. The sheer density of neutron stars forces us to confront some of the most perplexing and fundamental questions in physics. What holds this mass together against the immense gravitational pull? How can such matter exist under these conditions? These questions push the boundaries of our understanding. Neutron stars also introduce fascinating phenomena, one of which is the emission of pulses of radiation. These are produced by rotating neutron stars, which beam out radiation like a cosmic lighthouse. These beams of energy sweep across space at regular intervals, creating a pulsating signal. These rapidly rotating stars, called pulsars, they offer a unique cosmic clock, a regular and predictable source of radiation that can be observed from Earth. The precision of these pulses makes them an invaluable tool for scientists testing the limits of general relativity as well as other fundamental principles of physics. The regularity of the pulses provides a method to examine these theories in the most extreme environments known to science. Each discovery about neutron stars deepens our understanding, yet also reveals new contradictions or inconsistencies that fuel further inquiry. Every answer brings forth new questions. These discoveries not only expand our knowledge, but also highlight the gaps in our current theories, urging us to reconsider or refine what we think we know. As we study these stellar remnants, we find ourselves delving into some of the most profound philosophical considerations about the nature of knowledge and the limits of human comprehension. How much can we really know about the universe, given the complexity and mystery of these phenomena? Can we ever fully grasp the nature of gravity under such extreme conditions? The very existence of neutron stars forces us to confront these uncertainties and to push the boundaries of what is possible in scientific understanding. Neutron stars are more than just scientific curiosities. They challenge the essence of what we believe to be possible. In their dense cores, the normal laws of physics are pushed to extremes. The strong nuclear force which binds neutrons together against the powerful gravitational forces trying to crush them operates in ways we don't fully understand. The extreme conditions found in neutron stars, intense gravity, rapid rotation, and incredibly strong magnetic fields, present us with phenomena that defy our conventional understanding of matter and energy. These celestial bodies exist at the very end of the stellar life cycle, but even after their violent creation, they remain enigmatically active. Some neutron stars rotate at astonishing speeds, sometimes completing a rotation multiple times per second. As they spin, their magnetic fields interact with their surroundings, creating bursts of radiation that can be detected across vast distances. The fact that these neutron stars can emit beams of radiation with such precision and regularity has profound implications for the study of space-time and the fundamental forces at play in the universe. Moreover, neutron stars serve as markers in the grand cosmic hierarchy. They emphasize just how small and fragile Earth's existence really is in the grand scheme of things. Neutron stars exist in environments of extreme density and gravitational forces, offering a humbling reminder of the vastness and complexity of the universe. These cosmic beacons, with their powerful magnetic fields and their role in the formation and distribution of elements, place our planet in perspective. Tiny and transient, yet part of a greater, ever-evolving cosmic system. Neutron stars also provide a crucial role in the cosmic recycling process. The explosive death of a massive star through a supernova creates heavy elements such as iron, which are scattered into space. These elements enrich the surrounding interstellar medium, helping to create the building blocks for new stars and planets. It's this continuous cycle of stellar birth, death, and rebirth that drives the evolution of the universe. And neutron stars are essential to this process. They serve as both a graveyard for dead stars and a birthplace for new ones. The ultimate fate of these neutron stars is not always clear. Some of them may eventually collapse further into black holes, while others will continue to rotate and emit radiation for billions of years. But the birth of a neutron star often marks the creation of some of the heaviest elements known to science. When neutron stars collide, something that happens very rarely, but has been observed in recent years, they can create incredibly energetic explosions called kilonovas. These collisions can generate enough energy to forge some of the heaviest elements in the periodic table, including gold and platinum. The energy released in these events is so powerful that it can be detected across great distances in space. Kilonovas are proof that neutron stars are not passive remnants, but active agents in the ongoing cosmic cycle of creation and destruction. The materials and elements created in these collisions, iron, gold, platinum, and others, are scattered across the cosmos. This stardust forms the building blocks for the formation of new stars and planets. More importantly, these elements play a crucial role in the formation of life itself. The very elements that make up the Earth and the human body were created in these extreme events, making neutron stars not only important for the development of the universe, but also for life as we know it. In many ways, neutron stars represent the paradoxes and mysteries of the universe. They are the final remnants of dead stars, yet their existence is far from the end of the story. They are both the product of an explosive death and the catalysts for further creation. The elements they produce, the radiation they emit, and the energy they release shape the universe, ensuring that the cosmic cycle continues. And in that cycle, we find ourselves, tiny as we are, yet irrevocably linked to these distant, awe-inspiring remnants of massive stars. In essence, the study of neutron stars is not only a quest to understand these remarkable objects, but also a journey into the very nature of the universe itself. With every new discovery, we uncover more about the intricate processes that govern the cosmos, and with each new mystery, we are reminded that the universe is far more complex, beautiful, and enigmatic than we could ever fully comprehend. Neutron stars are a symbol of the endless quest for knowledge, a testament to the ongoing evolution of scientific understanding, and a humbling reminder of the vastness of space and time. Neutron stars are among the most fascinating and enigmatic objects in the universe. These stellar remnants, born from the cataclysmic deaths of massive stars, offer profound insights into the nature of the cosmos. When two neutron stars collide, an event called a kilonova occurs, a catastrophic yet spectacular explosion that releases an enormous amount of energy. This event is not only visually stunning, but also plays a crucial role in the chemical evolution of the universe. During the collision, nuclear reactions occur, producing elements far heavier than iron, elements such as gold and platinum. These newly formed elements are then ejected into the surrounding space, enriching the interstellar medium and contributing to the chemical diversity of the universe. The process through which these elements are created is known as nucleosynthesis. Essentially, it's the process by which lighter elements combine to form heavier ones, and it is most effective under the extreme conditions found in the heart of these catastrophic events. As the collision occurs, the temperatures and pressures become so intense that nuclear fusion reactions can occur, leading to the creation of these rare and valuable elements. The newly forged gold, platinum, and other precious metals are then scattered across the cosmos, blending with the gas and dust that exist in the space between stars. Over time, these enriched materials contribute to the formation of new stars, planets, and potentially even life. This role of neutron stars in cosmic recycling is vital. By creating and distributing essential building blocks for future celestial bodies, neutron stars are active players in the ongoing cycle of birth, death, and rebirth that shapes the universe. These processes take place on a cosmic scale, influencing everything from the formation of new stars to the development of complex planetary systems. Neutron stars effectively become the universe's furnaces, crafting the very elements necessary for the emergence of future generations of stars and planets. Without the contributions of these neutron stars, the chemical richness of the universe would be vastly different, and the creation of new galaxies would be stunted. Moreover, neutron stars are not only crucial for the material composition of the universe, but also for the dynamic processes that take place within galaxies. The life cycle of massive stars, which ends in a supernova explosion, is a key event that shapes the galaxies in which these stars reside. When a massive star reaches the end of its life, it detonates in a supernova, an explosion that releases an incredible amount of energy, much of it in the form of light and heat. This explosion also disperses a wide variety of heavy elements such as carbon, oxygen, and iron into the surrounding space. Neutron stars are often the remnants that remain after these spectacular explosions, acting as the dense cores that provide the foundation for further galactic evolution. The density of neutron stars is mind-boggling. A neutron star packs more mass than the Sun into a volume no larger than a city. In fact, their density is so extreme that a mere cubic centimeter of neutron star material would weigh as much as a mountain. This intense density creates conditions in which nuclear reactions can take place, leading to the synthesis of heavier elements, elements that are too large to form in the cores of typical stars. In the violent environments created by neutron star collisions, rapid neutron capture occurs, further adding to the creation of heavy elements, including precious metals like gold and platinum. In addition to their role in nucleosynthesis, neutron stars also generate powerful electromagnetic radiation, which can have a significant impact on their surroundings. Neutron stars emit radiation across various wavelengths, from radio waves to X-rays and gamma rays. As these emissions travel through space, they interact with the surrounding matter, including gas clouds and interstellar dust. In some cases, these interactions can trigger the formation of new stars. The powerful radiation output from neutron stars can act as a catalyst, igniting star formation in regions that might otherwise remain dormant. Neutron stars also possess strong magnetic fields, which can accelerate charged particles to near light speeds. These particles then create areas of plasma that interact with the surrounding interstellar medium, creating stunning visual displays of light and energy. These magnetic fields are not only responsible for the emission of radiation, but also influence the environment around the neutron star, shaping the behavior of matter in the region. The combination of high-energy radiation and powerful magnetic fields makes neutron stars dynamic agents of change in the universe, capable of influencing both the birth of new stars and the movement of existing matter on a grand scale. The phenomenon of neutron stars is not just limited to their role in nucleosynthesis or their electromagnetic output. Their interaction with the universe takes many forms, including the creation of gravitational waves. When two neutron stars orbit each other and eventually collide, they produce ripples in the fabric of spacetime, known as gravitational waves. These waves can travel vast distances across the universe, offering scientists a new way to study the cosmos. The merger of neutron stars, along with the associated explosion, is one of the most energetic events in the universe, releasing not just gravitational waves, but also a burst of electromagnetic radiation visible across great distances. Beyond the death of individual stars, neutron stars contribute to the grander narrative of cosmic evolution. When we look at the formation of new galaxies, it's clear that neutron stars play an essential role in shaping the very materials that go into the creation of planets and stars. The elements produced during the collision of neutron stars are mixed into the gas and dust clouds that eventually condense to form new celestial bodies. The birth of stars, and by extension the formation of planets, would not be possible without the heavy elements formed in these high-energy catastrophic events. In comparison to white dwarfs, another type of stellar remnant, neutron stars exhibit vastly different physical characteristics. White dwarfs are the remnants of stars with a mass comparable to the Sun. These stars end their lives by shedding their outer layers, exposing a dense core made primarily of carbon and oxygen. The pressure inside a white dwarf is sufficient to resist the force of gravity, preventing further collapse. This support, however, is not due to neutrons, but rather the electron degeneracy pressure, which arises from the behavior of electrons in a highly packed environment. White dwarfs, unlike neutron stars, slowly cool over time, their fading heat a reminder of the life they once had. On the other hand, neutron stars are formed from the remnants of more massive stars. When these stars exhaust their nuclear fuel, they undergo a supernova explosion, collapsing under the force of gravity. The pressure during this collapse is so intense that it converts protons and electrons into neutrons, creating an object that is almost entirely composed of neutrons. The gravitational pressure is balanced by neutron degeneracy pressure, which resists the collapse and allows the neutron star to exist in its dense, compact state. The comparison between neutron stars and white dwarfs highlights the influence of a star's initial mass on its final form. Stars of a certain size will end their lives as white dwarfs, while those of greater mass will evolve into neutron stars. Neutron stars and black holes are both extraordinary objects formed from the remnants of dead stars, but they represent different phenomena in the cosmos. While neutron stars are the dense cores left behind after a supernova, black holes are the result of an even more extreme collapse, where the core's gravitational force becomes so strong that it pulls everything into itself, even light. Neutron stars, on the other hand, remain visible, emitting radiation and interacting with their environment in dynamic ways. Neutron stars, especially those with extraordinarily powerful magnetic fields known as magnetars, represent the extreme limits of the universe's physical laws. Magnetars, a rare class of neutron stars, have magnetic fields that are 1,000 times stronger than those of typical neutron stars. This extreme magnetism leads to incredible bursts of energy, including gamma rays and X-rays. The powerful magnetic fields of neutron stars and magnetars influence not just their immediate surroundings, but also the larger structure of the galaxy in which they reside. In conclusion, neutron stars are key players in the cosmos, acting as crucibles for the creation of heavy elements, catalysts for star formation, and powerful sources of electromagnetic radiation. They are among the densest and most fascinating objects in the universe, and their influence shaping the chemical makeup and evolution of galaxies. By continuing to study neutron stars and their interactions, scientists gain invaluable insights into the fundamental forces that govern the universe, the birth and death of stars, and the very building blocks of life. Neutron stars are among the most enigmatic and captivating objects in the universe. These remnants of massive stars that have undergone catastrophic supernova explosions pack a density so extreme that a single teaspoon of neutron star material would weigh as much as all of humanity combined. They represent the final, compressed stage of stellar evolution, containing the crushed remnants of a star's core that has collapsed under the force of gravity. Yet, despite being incredibly dense, neutron stars are far from simple. Their unique features, such as their magnetic fields, rapid rotation, and ability to emit high-energy radiation, have made them focal points for cutting-edge research, shedding light on the most extreme conditions found in the cosmos. At the core of neutron stars lies an incredibly dense material, primarily composed of neutrons. These neutrons are packed together so tightly that the star's mass is confined to an area the size of a small city. However, this sheer density is just one piece of the puzzle. What happens within these stars remains largely a mystery, with scientists still speculating about the possibility of exotic forms of matter, like hyperons or even quark matter, which may exist in such extreme conditions. As neutron stars collapse, the forces at play are so powerful that traditional physics fails to fully explain the behavior of matter. These unknowns drive ongoing research, prompting a deeper look into the fundamental laws of physics, which could reveal new aspects of reality itself. Among the most intriguing aspects of neutron stars is their ability to emit powerful beams of radiation. Some neutron stars, known as pulsars, rotate rapidly and emit beams of electromagnetic radiation in sweeping arcs, much like a lighthouse casts its light across the ocean. However, unlike the steady light from most stars, the radiation emitted by pulsars is visible only when the beam is directed towards Earth. This creates a unique pulsing pattern, a phenomenon that distinguishes pulsars from other celestial bodies. The speed of their rotation, combined with the intense magnetic fields they possess, makes these pulsars incredibly efficient at emitting high-energy radiation, including X-rays and gamma rays, which adds to the allure of these cosmic objects. In contrast to the pulsar's radiant pulse, black holes, another type of fascinating stellar remnant, do not emit radiation in a conventional manner. Black holes are notorious for their ability to capture everything within their gravitational grasp, including light itself. Beyond their event horizon, not even light can escape. However, black holes can indirectly emit radiation through a process known as accretion. As material spirals toward a black hole, it forms a swirling disk that heats up to extreme temperatures. This hot material emits X-rays before it is pulled into the black hole, but the radiation is not intrinsic to the black hole itself. Instead, it originates from the intense interactions of the accreting material. This is starkly different from the radiation emitted by neutron stars, where the origin of the energy lies in the star's rapid rotation and dense core. Despite their differences, neutron stars and black holes share one key characteristic. Both push the limits of our understanding of the universe. While black holes are defined by their immense gravitational pull, neutron stars captivate scientists due to their extreme physical conditions and the behavior of matter under pressure. Their internal structure, along with the intricate dynamics of how they spin and emit radiation, is still the subject of intense study. Furthermore, the magnetic fields of neutron stars are far stronger than those found on Earth, trillions of times more powerful, in fact, and the mechanisms behind their generation remain largely unknown. Researchers continue to probe how these magnetic fields are sustained and how they contribute to the phenomena observed in pulsars. In addition to their magnetic fields, neutron stars present another captivating puzzle: their life cycle. While it is well established that these stars are born from the collapse of massive stellar cores during a supernova explosion, many questions remain about the precise mechanisms behind their birth and evolution. Scientists continue to investigate how neutron stars lose energy over time and how this influences their eventual fate, including the possibility of neutron star mergers, which have been observed to produce gravitational waves. These ripples in space-time provide valuable insights into the nature of neutron stars, their behavior under extreme conditions, and the structure of the universe itself. Moreover, the collision of neutron stars creates gravitational waves, ripples in the fabric of space-time that provide an entirely new window into the universe. When neutron stars collide, they send shockwaves through space-time that are detectable by advanced observatories. These waves offer researchers the chance to study not only the physical properties of neutron stars, but also the fundamental nature of gravity. The observation of neutron star mergers has already led to significant discoveries, including the detection of heavy elements like gold and platinum, which are thought to be formed during such cosmic events. But the mysteries of these collisions go even deeper. For example, there is growing interest in how these events might be linked to the existence of dark matter, one of the most elusive and poorly understood components of the universe. As technology continues to advance, so too does our ability to observe neutron stars in greater detail. The development of next-generation telescopes and detectors has revolutionized the way scientists can study these cosmic wonders. With more precise data than ever before, researchers can test theories related to the behavior of matter at ultra-high densities, the nature of nuclear interactions, and the intricate dance between gravity and electromagnetic forces. These observations are not only shedding light on neutron stars, but also challenging our understanding of the universe, pushing the boundaries of astrophysics to new heights. Neutron star research is, therefore, an ever-evolving frontier in the quest to unlock the secrets of the universe. With every discovery, whether it is the detection of a new pulsar, the observation of a neutron star merger, or the mapping of their magnetic fields, scientists are drawing closer to a deeper understanding of the forces that govern the cosmos. The study of neutron stars is more than just an exploration of one type of stellar remnant. It is a journey to the very heart of the universe itself, where the rules of physics are pushed to their breaking point and where every answer leads to new, even more profound questions.